Hello, everyone. So we are going to resume the talks. Please take a seat. Yeah. So in this session, we will have three great invited talks. And the first one is by Jordi. He's going to talk about the toolings to build a zKEVM. Okay, yeah, sure. I already told them, yeah.
Hello, everybody. I'm Jordi Bailina. I'm the technical lead at Polygon Hermes. Here in Polygon, we are building a zKEVM, fully EVM compatible rollup. And I'm going to explain a little bit in Rick's presentation all the tooling that we have been building for to build this zKEVM. And it's a tooling that actually is open source and anybody can use for building other things. So, well, let's start. Explain a little bit what we have been done. What's a ZK rollup, or at least I think most of you know already what's a ZK rollup, but I want to maybe clarify things how the ZK rollup will work. So from the user perspective, mainly what's going to do is going to generate transactions. In this case, it's Ethereum transactions, normal Ethereum transactions. But instead of sending them to the blockchain, they will send it to a sequencer. This sequencer can be centralized or decentralized, but at the end, it's like a role that will take these transactions, and they will publish, and they will send these. And they will publish these transactions on chain. These transactions are just a row of data. And the thing is that there is a kind of a consensus, or is so everybody knows how to process these transactions. So there is an implicit state. So you process these transactions, and you don't know exactly what state. So the blockchain don't know what state, but everybody can process these transactions in a deterministic manner, and they know what's the exact state of the blockchain. So, and later on, it's going to be a prover. It's going to be another entity that's going to take these transactions, and it's going to compute this state, and it's going to prove that actually this state is the state that anybody can compute. But this state is going to be explicit. So it's going to put this state on chain. That means that at this point, because the chain now what's the current state, maybe, for example, you can withdraw funds. Okay? So this is the splitting part is sequencing in one side, and then the prover. But the prover cannot do anything. They are just taking transactions that are already on chain, that they are already processed, they are already final, and the only thing that's doing is just running this and generating a proof that the current state is this one. Okay? So, yeah, so what's a prover? And this is probably the difficult part, and this prover is the difference between an optimistic rollup and a ZK rollup. Okay? And this prover is, at the end, is a computational proof, is that when you are taking all these transactions that are available because they are on chain and you process them, the new state is this one. So it's a deterministic circuit, and we'll try to build a circuit with zero knowledge that's processing these transactions. These transactions are Ethereum transactions with RLP, with the CDSA. They can deploy smart contracts. They can call smart contracts. You see, it's complex. So this circuit, it's okay. Let's build this circuit, okay? But this circuit is not an easy circuit, and the difficulty of this is how we build this circuit. First approach is, okay, let's use Circum, okay? But you know, it's tough. You know, it's just, I don't know how many constraints, but it's not practical, okay? So because, you know, complexity is so huge that you cannot think in the traditional toolings like Circum. Okay, so the approach that we built is, Circum, you can understand Circum very much as if we see the hardware simul, or it's Circum is just, you have like gates, like hardware, or in this case arithmetic gates, but in electronics would be, you know, AND gates or OR gates, and you build a circuit that's linear, you know, that just you put the inputs and you have gates, and at the end you have the output, okay? But with this concept of IOPP, so this concept that was introduced by Stark's people and so on, the idea is that you can you introduce like the clock. So the idea is that you don't have a big circuit, you have a small circuit, and then you can repeat this circuit many times, and you have a clock. And you have this concept of a state machine. So you have something that's state values, then you apply these electronics, and you compute this new these new state values. Okay, so the electronic is an electronic that's repeated many times. Okay, so this is the basic of a state machine. So the approach that we follow is, okay, because we have state machines, then we can build processors. Processors at the end, if you see what's a processor is a state machine. That's every clock, you are changing the state from one to the other. So the idea is, let's build a processor, a simple processor, something that's doable, okay, with this technique. And then we run a program on top of this processor that actually does what the EVM does. So it just takes this is a program that's just taking the transactions as input, they hash them together, they do all the logic that Ethereum is doing, which is complex, okay, but then it's a processor, we just run a program, and then we have this circuit. Okay, so this is the idea. So we have to build a processor. So this is like building a hardware in this similitude. Of course, we don't have transistors here, we have polynomials, but at the end is we need to design these state machines, to how the processor evolves, and then we have a ROM, we have a program. It's an assembly that's running on top of this processor. Okay, so here is the language that we build for this is PIL. Okay, PIL is a language for building these state machine transistors. Okay, so I want to explain a little bit in this presentation how PIL works, because I think this is the tooling part and so on. So for this, I'm going to put a simple example. This is a traditional example. It's something that's very used in the literature. That's the Fibonacci series. So I'm going to put a specific problem here. So we are going to work in a finite field. This is a small frame field compared to the one. This is a 64 field. This is called Goldilocks. And this is one of that's very useful because in the Starks, working with these finite fields, it's very convenient. I think next presentation from Daniel will talk about that, and it's very convenient. But the idea is that the example that we want to build is, okay, I want to prove that I know two numbers that when I apply a Fibonacci series 1,024 times, I get this number. So this will be like the public input, in this case, a public output of the circuit, and then it's going to be two private inputs. It's the first two numbers, and then I compute a circuit. Okay, the circuit, if I'm doing in Circom, it's quite straightforward. I'm going to jump on it. Okay, but let's do it with a state machine. So how I convert that in a state machine? Why it's important? Because Fibonacci series works very well as a state machine. So in this case, I have two state machines variables. Okay, before last and last. And the idea is that I can define the state transition function. So how I decide to define the state transition function? Well, I'm just saying that the before last is going to be the last. So I'm just moving this from here to this here. And in this one, I'm just adding. So the last is going to be the addition of the last two. So here is I'm just defining a normal state transition. It's very simple state transition function. Of course, a processor is going to be much more complex, a state transition function, but it's going to be a state transition function. Okay? So here is the thing. So this is what I need to define, okay? Here I have some problems here, is that, this is going to be converted to polynomials. The polynomials are going to be, these are the evaluations. So the state. So the trace of the state is going to be the different evaluations of a polynomial. It's a polynomial that at the different roots of unity is evaluated to a different value. So I have, in this case, I have two polynomials, A before last and A last, which is going to be the state transition function. And what I'm saying is I'm defining this polynomial in the next root of unity, what this root of unity happens. Okay. So, and the problem of this is when we're working with these roots of unity are cyclic. Okay, so we need to do some tricks especially for the boundaries, especially from the last to the first. Okay, this state transition function works well from here to here, from here to here, from here to here, but does not work well when I'm going from the last one to the first one because this is cyclic. So here I'm just doing a simple trick. I'm just defining another polynomial. In this case, it's not it's going to be a fixed polynomial. It's a polynomial that can be pre-computed beforehand. That's going to be 0 everywhere, but 1 in the last one. This is the Lagrange polynomial, the last Lagrange polynomial of this field. Okay. So if I write that in PIL, then I'm just doing this one. So here is like this equation of what I'm saying is that this must be equal to this. So the subtraction must be 0, but I'm applying that only when it's not the last one. So so everywhere except for the last one. Okay, and exactly the same here, but for the other state transition function. So this is how the thing. Here at the beginning, I'm defining this constant polynomial, so a pre-computed polynomial, a polynomial that's computed beforehand, and then the committed polynomials that for every instance, for every time that I'm executing for a different public, so every time that I'm executing a different, then these are the polynomials that are going to be committed. Okay, here in the end, I'm defining the public. I'm defining also the public output. I'm just saying, and here I am adding the boundary constraint here. I'm just saying that when it's last, so in the last, it's only when it's the last, then the last polynomial must be equal to this public output. Okay. So this is very much how PIL works. Yeah.
Where are you capturing the initial conditions? Where are the initial conditions?
Well, the initial conditions they are private inputs. So you want to prove that you know this that you know two numbers. That when you compute them together, when you but they are private inputs. So here I only define public inputs or outputs. So I just define public places. Here I'm defining where is this place, but this is just for. It's not any constraint here. It's just where you get the value from, just because it's convenient that the prover also gives you the public outputs. So here you just define where you are getting, but it's not a constraint itself. Okay. So very easy. So we have the PIL. So when we have this kind of systems, what we need to build? We need to build three things. Just three things. We need to define three things. When you are building a new circuit that works with PIL, you need to define a PIL. So we need to define which polynomials are you going to use and what are the relationships of these polynomials. You need to write a code to compute the pre-computed polynomials, the constant polynomials. It's a code that you're going to run once at the beginning, before, once when you are setting up the circuit. And then you need to build another code that, for a given input, actually is computing the committed polynomials. Okay, so you have three pieces: the PIL, the code for computing the pre-computed polynomials, and the code for the witness computation for computing the committed polynomials, in there. Okay, so you can see the code may look something like that. The constant to build the constant is just a loop that is going to be 0 everywhere except for the last one. So it's a very easy code in this case. The actual code, the executing code, is actually the ones that's here is computing the before last and last. It's computing the state. It's computing the trace of the state of U1. It's computing these committed polynomials. Of course, here you have an input because depending what you want to build, you will have some input. Here we are just printing out. And that's it. That's all what you need to do to build a system with state machines. Why? Because after that, we have a component that's PIL Stark, but could be any front end in front that's just taking these polynomials and building a proving system. So building a proving system, so a system that will generate a proof automatically for you. Okay, so that's what PIL Stark does. It just takes these three pieces, and with this, it generates proving. So in this case, a Stark proof, a Stark prover, and a verifier by itself. But it could be in a Stark, but it could be also with a Kate commitment or whatever proving system in front that you have. Okay, so the only thing you need to define, and this is specific for the circuit, is this. Okay, here in the PIL. This is for basic identities, but PIL can be is extended with more sophisticated constraints. Here, for example, I can specify that two polynomials are a permutation on each other. So I'm saying that A is B, because I can have a permutation. I can also define permutations in multi-columns and with a selector. So I'm just saying that the columns that are set that's where the selector is 1 are the same that the columns that are selected in 1, but in different permutation. So that's one thing that I can do. I can do lookups, which is just all the values in the A must be in the B, but can be maybe some value that's not here but is here, or there can be some repetitions, some values that are repeated in the first one. It's just an inclusion check, and it can also be with multi-column. So multi-columns and with selectors. I can say only the rows that are selected must be included in the rows that are selected in the right side. Okay. Then what else can I do? I can do copy constraints. This is so I can say, for example, just taking a polynomial, and I want to say I want to force that the first value, the fourth, the fifth, and the seventh are exactly the same, or the second and the for last is the same. So how I'm doing that, I'm just defining a constant polynomial, which is the identity polynomial, but just permuted. So just for example, if I want this is 1, W3, W4, W5, what I'm just doing is I'm just doing just a cycle. So I'm just putting here 1, W3, W4, W5. But they are just rotated on each other. So this polynomial defines what are the copy constraints that are using. People that know Splunk, it should sound very familiar because that's what actually Splunk does. Okay? I can do that in one column, but I can do also this in many columns. So I can copy constraints between different columns. Okay? And with this, for example, I can define Splunk. This is an example of PIL, just to implement Splunk. But this is just a simple example. Okay? So here I can have the committed polynomials, ABC. People that know Splunk should be familiar with that. We have the permutation constraints that define the copy constraints, how the circuit is connected one each other. Here with the queues, I have the Splunk gate, the standard Splunk gate, but I can define easily a custom gate, or I can define whatever I want here, something like this, a lookup, or this is very flexible in here. And here in this case, I also define a public input. Okay, but this is, you see that Splunk is just a specific example of the systems that you can build with PIL. Okay. For this is, well, for example, one thing is interesting, we extended CIRCOM. I don't know, many of you know CIRCOM already, but we extended CIRCOM, for example, to defining custom gates. Actually, in CIRCOM, you don't do anything on custom gates. The only thing that you do in CIRCOM is you define something that's a custom gate, is something that you can export. So then it needs to be something else after that takes these custom gates and convert that to some polynomials in Splunk. But CIRCOM allows now to define custom gates so they can generate different blocks and connect custom gates. Okay? So yeah, when we have this, so we have all this our system, and that can be with block apps, with whatever, so all the information, and then we just put the PIL stack, and this generates the proving part. But not only that, so it's not generate only the prover and the verifier, but it also generates a prover, it generates a verifier, but it also generates, the PIL stack can also generate a CIRCOM circuit that verifies the stack. Okay, and this CIRCOM circuit can be in Goldilocks, so to generate another stack, so I can get the CIRCOM and generate another stack that goes in Goldilocks, or can be another circuit that is in the BN curve, so that generates a gross 16 or a Splunk where I can verify it on chain. So here I have all the recursion, so the tooling for doing the recursions, so verifying a stack with another stack, or verifying a stack with a gross 16. Okay, and this is just generating CIRCOM and so on. This tooling, PIL and CIRCOM, the cool thing is that you can work so you can work with both tools, and you can get the best thing. Sometimes, depending on what you want to do, it's better to do if you want to do a Ketchak, for example, it's good to do it in a circuit, because Ketchak is very much a circuit. But if you want to do a processor, maybe it's better to do it with PIL. And the idea is that you can combine them together. Okay, and this is what we did in the zKEVM. We have all the recursion, as I mentioned, verifying the start with row 16. Okay, but okay, this is very nice. This is a theory, but okay, how we build the zKEVM actually? Okay, so that's well. Let's start doing. Let's start doing it a little bit. Okay, so the first thing is we need to implement a processor. Of course, it's a very simple processor. It's a processor that doesn't do very much. What's doing this processor? We have a processor have registers. In the case of the zKEVM, these registers are going to be 256 bits, which is actually our 8 polynomials each register and so on. Okay, so here processor needs to have instructions. Okay, so in every clock I'm going to execute an instruction. In our case, the instructions are So it's not one polynomial that's the instruction. There are many polynomials that conform, that are all together are the instructions. And this polynomial, so these polynomials can be, this is what's in white in this slide, okay? So it's like, you can select, so like in A, in B, in C, in D, these are different polynomials that can be 0 or 1. And here, what I'm doing here mainly is I'm selecting the value of one register. I'm putting like an intermediate register, which is operator, and then I can set the value of this operator to register to another register. For example, if I want to do a move between A and B, then it will be an instruction that will be in A is going to be 1, all the rest is going to insert going to be 0, set B is going to be 1, and set A, set C, and set D is going to be 0. Okay, you can see the pill how it works. So the OP is A times in A plus B times in B. So if in A is 1 and the other is 0, OP is going to be A. Okay, and here I'm just setting. So if the set A is 1, I'm going to set whatever is in the P. If set A is 0, I'm going to keep the old value of the registers. Okay. So with this, I can do moves. Here I have, as part of the instruction, I have a const that I just add. This is for immediate values. So in a normal processor, you want to put, sometimes you want to put a 3 in register A. So you put const to 3, and you set to register A. Okay. And the other important thing here, and this is very specific to the zKEVM, is the freeing. So we have a special. It's not a register. Well, the idea is that if the instruction in freeing is 1, that means that the prover can put any value, and it can put any value to the system. So this is non-deterministic. So it's like you have an instruction that allows you to put in the system any value there. Okay? This is a little bit dangerous because, okay, you can put any value, but then it's not deterministic. But the idea is that then later on, you are verifying that this value is correct. For example, if you want to do a division, you put the result in the division, and in the next one, in the next instruction, you are going to check that actually this value plus the denominator is the numerator. Okay, 3 minutes. Okay, yeah. Okay, that's too much. Okay, we have you have the here in the processor we have conditional jumps. Okay, so because we want to jump one, so we have a program counter to jump from one to the other. Here we have well, this is how we execute the ROM. Okay, one thing is the program that's constant. The other thing is the execution trace, is which instruction you are executing in each one, and we are forcing that you are executing a ROM, that you guys you are not executing the instruction that you want. Okay. If we have memory, I'm not going to enter here, but we can have a system that's in memory. And here the idea is that we can have also systems that are like subprocessors, another processors that are so I can have like another subprocessors that are computing other things. For example, I can have an arithmetic state machine, a binary state machine, or other processors that are other state machines, and then with via lookup, I'm verifying one thing in the main, but I'm really computing everything in another state machine. With this, the system have RAM, ROM, storage. We have also here binary implementations. We have also ketchups and hashes that are things here. So here in the electronics, we added everything that's needed, that's required for the zKEVM itself. So sometimes there are complex things that we implemented in hardware instead of doing in software. So it's a kind of a tailor-made hardware for running. It's like building a processor tailor-made for building a specific program in this case. Okay. And here on top of here we have the ROM. Well, the ROM is just a program that's executing the zKEVM itself. Okay. And once we have the ROM, then we convert to PIL, and here we have a structure. So here we have the proof. Okay. The proof here is that we have a main proof, which is the one in here. We can aggregate these proofs with one proof to many proofs to a single proof, and then we convert that to growth 16, just using the PIL start that we mentioned before. Okay. Proving costs. Okay. Right now, well, we are running right now a test. We have a test. We have a test network right now that you can test that with the prover, everything running. The current prover in the system you can test. You can deploy smart contracts. You can just use Remix to deploy in there and use it as a normal EVM. The proving cost right now is probably the biggest, in a $9 per hour AWS. It takes about 9 minutes to compute a 4 million gas proof. Okay, that is a very huge. This is a huge machine. Okay, we expect this. At least we believe that we can even get one order of magnitude better to this. But even with these numbers, the cost per transaction is going to be sub-cent on there. So it's practical. But there is still a lot of margin to improve here with GPUs, doing better designs, better circuits, and so on. Okay. We are also running all the testing, so we are using the Ethereum test suites to be 100% compatible with Ethereum. Right now, we are passing 97% of the test. There are still some edge cases that we are working on that, but it's getting quite close to this. So this is for the test updates. We have the public testnet that anybody can test. Everything is open source, so you can take a look and check and review and run it and work on that. Okay. And yeah, you have the testnet. You can run it here. So that's my presentation. Thank you. We're running out of time, right?
Thank you. I guess given the time, let's take the questions offline. Let's thank the speakers again. So, next one will be talk by Daniel. Yeah. Okay. So. Yes, please.
Okay, thank you. So I'm going to be talking about BigInt Techniques for ZK. But first, I just wanted to give a bit of background about what we're doing at Polygon 0. So Polygon 0, we're building this zKEVM, and it's based on this technical stack built around Plonky 2. So we have a Stark library first called Starky. The Starks are a very good fit for virtual machines like the EVM because we're doing the same thing over and over again. And then when we want to aggregate multiple transaction proofs, then we need recursion for that. So that's where Plonky 2 comes in. Plonky 2 is an implementation of Plonk with a bunch of custom gates to optimize recursion. And since our implementation of Plonk is also based on Fry as the polynomial commitment scheme, it shares a lot of the same components with Starky. So we really have one stack here where we use the same field, we use the same polynomial commitment scheme, et cetera, for both. And the field, as Jordi mentioned, is this small 64-bit field, which we call Goldilocks. And that's one of the keys to how we make proofs so fast, is because like doing one multiplication in this field only takes about 2 cycles on a typical CPU. So one of the problems that keeps coming up over and over for us in different settings is we're working with this prime field, and arithmetic in that field is very direct and very efficient, but often we need to do some other type of arithmetic. For example, our zKEVM, we have to simulate 256-bit multiplication, modular multiplication, and so forth. We also have to deal with things like ZKP signatures. We're not working over the ZKP field, of course, so we have to somehow simulate that. And not for Plonky 2, but a lot of other recursion schemes involve some kind of non-native field arithmetic. So, of course, we could just apply classical algorithms like grade school multiplication, but those are very expensive in ZKPs, so we're looking for something more efficient. And here we take some inspiration from this classical like grade school trick called casting out nines. And what we do here is this is about verifying an identity. So it's not about computing a multiplication, but it's if we already have the result, maybe from a prover, then how do we check that? And the idea is that we take each number and just add up its digits in order to shrink the number. And we keep doing this shrinking process until we have this tiny numbers at the end, like 5 = 5, which is trivial to check. But in essence, what we're really doing here is instead of testing for equality, we're testing for congruence mod 9. So the left and right-hand side should be congruent mod 9 if this test passes. Of course, congruence mod 9 does not imply equality. So on the right here, we have a case where the two sides are congruent mod 9, but they're not equal. So obviously this isn't good enough. We're still missing something. I mean that is to say, this is a probabilistic check. We can get maybe some confidence that the answer is probably right, but it's not good enough. So the idea here is, what if we add additional moduli? So instead of just checking congruence mod 9, we can check congruence mod 10. That's actually even easier, because for congruence mod 10, every digit disappears except for the least significant one. Congruence mod 11 is also pretty easy. Then our base is 10, so base is congruent. 10 is congruent to -1, so basically our weights are 1 and -1. It's pretty easy to shrink numbers that way. And let's just suppose that we test mod 13 as well. So now we know that all 4 of these moduli divide. We have this expression which should equal 0. And we know that all 4 moduli divide that expression. Therefore, their least common multiple also divides that expression. In other words, we can say that this identity holds in terms of congruence mod the LCM. And if we can pre-compute this LCM, since we only do that once, and this LCM happens to be this 5-digit number, 12,000 and something. And finally, in this case, we can infer equality at the end, because we can easily see that we're multiplying 2 digits by 2 digits, so the result couldn't possibly be large enough to overflow this modulus. So when we have that sort of upper bound, we can infer that congruence does imply equality. So taking a step back and moving away from that specific example, but let's state it more generally, we're doing some kind of big num multiplication where we have 2 inputs, x and y. These are both big nums in some base b with n digits. And then we have a purported result coming from the prover, which is 2n digits. And we can interpret these, like x, y, and z, we can interpret them as a tuple of digits, or we can interpret them as the larger integer that they represent. And the mapping between those two encodings is given by this simple summation, where we're basically just adding up each digit of a big num with its appropriate weight. And we can also describe the product with a similar summation like this. X times y is basically a summation of all of the intermediate products given by the Cartesian product of our 2 tuples. And now the idea is we want to check that this summation for z is equal to this summation for x times y. But we have the problem that these summations are too big. We're working with a 64-bit field, so we can't directly do this. We'll quickly overflow our field if we're dealing with, say, 256-bit integers. So how do we shrink this so that things fit in our field? So the idea now is we take those summations that we saw before, and we take these constants, b to the power I, and since we're testing for congruence mod some modulus m, we can shrink the constants by, and this happens during pre-processing or pre-computation. We take all of these constants and reduce them mod m. And now we have these 2 summations with smaller weights. So practically speaking, m might be about 20 bits. And then if maybe our base is 2 to the 16, then we can compute one of these summations, and the result will fit in our 64-bit field. So yeah, let's use z prime and x times y prime to represent these 2 partially reduced summations. And then we can easily come up with upper bounds on these 2 expressions. And as long as these upper bounds are smaller than our native field P, then we're okay. We won't overflow. So taking a step back for a minute, we started with the problem of checking x times y equals z, and then we converted that to, let's come up with a set of moduli m, and for each mi in that set, let's test for congruence mod mi, because that would imply equality as long as we have the right bounds. And then we applied these partial reductions in order to shrink the two sides of that congruence test. But we've only partially reduced these quantities, so in general they won't be equal. We still have to check that they're equal mod mi, and to do that, we have the prover tell us basically how many times it wraps around. That's the variable si, is how many times do we wrap around m. But si will be small now because we've already shrunk the problem and we're dealing with small quantities. But ultimately, we're working with a like arithmetic mod p, so we can't directly test the third expression because the third expression is an integer relation, and we can only test for congruence mod p. But luckily, it ends up working out because we can argue that we can't possibly overflow p because our upper bounds imply that this quantity is just not large enough for overflow to be possible. So we can just test this mod p as usual and infer equality from that. So that was the basic technique. There are a few tricks we can use to optimize it further. So one thing we can do is, like typically we would come up with some set m of moduli that might be prime or at least coprime because we want their least common multiple to be large. But then instead of just picking a bunch of random coprime numbers, we can add in some special moduli, like 9 or 10, which we saw in base 10. Those are very convenient. And in our context, one of the most convenient moduli is our native field order p, because then like checking for congruence mod p is trivial. We just evaluate both sides, and we in our arithmetic circuit, and then overflow doesn't affect congruence mod p. Doing base b or a power of b is also very convenient. That's analogous to testing congruence mod 10. If we're working mod 10, we just look at the last digit. And there are a few more special cases we can use to shrink the problem a bit further, and then we end up doing less range checks that way. There's also a probabilistic variant of this, which was actually Jordy's idea, the previous speaker. And the idea here is instead of just picking instead of picking a small set of moduli m, we can pre-compute a much larger set and then take a random sample of that. So if we're thinking about base 10, this would be like, well, I don't want to always test for congruence mod 9 because then the prover might craft a solution that happens to hold mod 9. But if I pick, maybe I pick 9, maybe I pick 10, maybe a whole range of integers, then I can argue that it's unlikely for the prover, like if the prover gives me a wrong answer, it's likely that I'll catch it. And this is sometimes cheaper. It has slightly different costs. So depending on our security target and all of our parameters, this can be a bit cheaper. That's about it. It's a pretty simple technique, and we've gone through most of the math already. There are a few more details that are in this ePrint if anyone's interested in going a bit deeper. Thanks, and happy to take any questions.
We have time to take a few questions. Are there any questions from the audience? All right. Then, yeah, and if you have further questions, feel free to approach him offline. Yeah, thank you. Okay, and next we'll have here from Scroll to talk about their zKEVM design. Yeah. So, full screen out.
So hello everyone, my name is Ye. Today I'd like to talk about zKEVM design, performance, and some interesting challenges we met when we are building our zKEVM. So before diving into more detail, just a high-level quick introduction of what is Scroll. So Scroll, in short, is a scaling solution for Ethereum. And we are building a general-purpose layer 2 platform that inherits security from Ethereum, but all the transactions happening on Scroll are much cheaper, faster, and we have higher throughput. And more specifically, we are building something called EVM equivalent ZK rollup. So two things. One is that we are based on ZK rollup, which is considered to be the most secure scaling solution based on zero-knowledge proof. And second is that we can support EVM inside our ZK rollup. It's not specifically to one language like Solidity, but we can support everything that's running on EVM, including all the toolings around. So the development experience on Scroll will be exactly the same as Ethereum, and that's exactly what we want. And before diving into more detail, let's start with the traditional diagram of ZK rollup and why zKEVM is important here. So the idea behind ZK rollup is that instead of sending all the transactions to a congested and expensive layer 1 and reach some consensus, you send all the transactions to one off-chain and centralized node. And this node will run some magic, like zero-knowledge proof algorithm and generate a very small and sustained proof high. And on-chain verifier only to verify this proof without re-executing all the transactions. So this is the magic. And to build something general purpose, you need to handle arbitrary type of transactions. So you can't have some like fixed, for example, like you have some circuit for DEX and for lending protocol. You can't have any fixed circuit because all the transactions are interacting with different smart contracts. So you need this zKEVM to handle arbitrary EVM transactions. And so from a high level, zKEVM can prove arbitrary, like a batch of EVM transactions are correct using one ZK proof. And technically speaking, zKEVM consists of a set of circuits, and with all those circuits, you can prove that EVM is executing correctly, and then you can prove that all the transactions happening on EVM is correct. So to build a zKEVM, let's take a deeper look at what you really need to prove. So let's start with the initial state, like you got a state root here, and after receiving one transaction, and the node will run this transaction over EVM. So EVM is a stack-based virtual machine which Ethereum used to process transactions. And the EVM will load bytecode to the memory and use the transaction as part of the input. And the EVM will execute this bytecode from start, opcode by opcode. So you will result in something called execution trace, which is a sequence of opcodes you are really executing for this specific transaction. So because your transaction, you can deterministically get one unique execution trace. And during this execution trace execution, because you need to write to your state, so you will result in a different state root prime. And so this is your computation. And now let's take a look at what zKEVM and how it's function here. So zKEVM, intuitively, is proof for EVM execution, right? So the computation spec for zKEVM should come from Ethereum virtual machine. So we use EVM as a computation spec for zKEVM. So zKEVM has opcode circuits and everything that's needed in EVM for writing your constraints. And the public input of zKEVM is that your old state, your new state, and a batch of transactions. So the statement should be after applying n transactions, you get this new root prime. So because the verifier don't care about the execution trace and what's happening on, it only cares about the result. And within this zKEVM, you are using your execution trace as a witness. Because zKEVM need to, within EVM, the inner logic, you need to prove that there exists some execution trace, which is uniquely unrolled from this transaction, and it's valid, and it's consistent. So this is a high-level intuition and background for zKEVM and how it functions. Now let's take a deeper look at how you really design such a zKEVM. And so again, as I mentioned, to prove a transaction is valid, you need to prove that execution trace is valid. But this is not enough, right? Because it only contains your opcode you are executing for each step. So you need to unroll this smaller execution trace into a very large execution trace table, which contains more of the information as a witness. So let's take a look at what this execution trace table look like. So for each step, you will have 3 different type of variables. So there is step context, there is a key switch, and there is opcode, some opcode specific witness. So for example, step context contains when you're executing this step, what's your context? What's your code hash, what's the gas used, what's your program counter, what's your stack pointer, and all the context variable here. And within this key switch, it indicates that what this step is used for, right? So for example, it contains select the opcodes or the error cases. So within this green area, only one variable will be non-zero, so that you can easily know that what this step is used for. For example, if it's add, then you put this as add to be 1 and everything else to be 0. So it's binary just for selecting what this step is used for. And for opcode specific witness, it means, for example, if you are proving for add, then you definitely need to prove a plus b equal to c. You need to put all your operands and some carry, and maybe you chunk that into some leaves, and you put all the opcode specific witness there. So this is how you are generating the witness and how this execution trace table look like. And now let's write down some real constraints to constrain this execution trace table and prove that this execution trace is valid. So for step context, what it's saying is that if it's add opcode, then pro counter plus 1, and then step pointer plus 1, and the guess consumed plus 3. So it's basically proving that two steps are consistent. Like after executing step 3, you move to step 4 correctly with the same context. And the key switch indicates that within this green area, the value need to be binary, like either to 0 or 1. And adding them together, you get 1, which means only one variable will be open and put into 1. So one step can only prove for one certain type of opcode or error cases. And for opcode specific witness, it's saying that if it's add, then you apply this add constraints to that. So this is a general view of how you constrain each step. But that's not enough, right? Because another thing you need to prove is that because it's a virtual machine, when you are proving for add, you need to pop 2 elements from your stack. You need to prove that the elements you popped from stack is previously what you pushed, right? So you need to prove that operands are consistent. So how we are doing this? So in EVM circuits, we didn't handle this logic. We just look up the operands into a lookup table. So there is a magic. Imagine that there is a magic lookup table containing all the correct entries for each step, and it's ordered correctly. And then in EVM circuit, you just prove that, okay, so this operand at this certain step belongs to this table, and that's it. So EVM circuit doesn't handle any read and write consistently, but it only proves that this operand exists in this table. And now the question becomes how you are constraining that this table is generated correctly. So what we do is that we have a separate RAM circuit to constrain that all the entries in this lookup table is correct. The memory read and write are consistent with what you put previously. And so you will have a separate circuit for that. And similarly, when you are another trick you can play here is that because EVM has so many ZKPM-friendly opcode like catch and some very hard opcodes, you can't put all your witness into a tiny area. So what you do is that you just directly put your input and your hash output as a result and in this area, and then you do a lookup. You look up this pair input and hash output in a hash lookup table. And again, assume that there is some magic table which contain all the correct entries for input and output hash pair. And you just prove that if this input and hash output belong to this table, then you know that it's correct. And again, to constrain this table, you will have a hash circuit proving that all the entries in this hash lookup table is correct. So you can use one circuit to prove for repeated logic, multiple hashes, and separate from EVM circuits. So now let's take an overview at what the ZKEVM circuit architecture look like. So you start with some EVM circuits which constrain each step and state transitions. And then you have a bunch of magic tables. Like for example, you have fixed table for bitwise check, for range check, and you have catch table storing all the correct entries for hash, and you have RAM table for stack memory and storage operations. You have bytecode table, transaction table, all those tables. And in EVM circuits, every time you meet something really complicated, you just look up, and without really checking anything. And then for each table, you need to have circuit to constrain that this table, all the entries in this table is correct. Right, because fixed table is pre-processed. Catch table, you need to have catch circuit. You need to have some Markov potential tree circuit for RAM table, RAM circuit, and the ECDSA circuit, and then you do lookup. So this is what the ZKEVM circuit architecture look like. So every time when you mention ZKEVM, it's actually a set of circuits, and some circuits are constraining some table, and those tables are connected. Now let's take a look at the performance, because many people are complaining that, okay, so it's so complicated, why you are building this for EVM, and the performance must be terrible. So let me introduce what's the performance, and what's the proof generation time, what's the circuit layout really look like. So in Scroll, we are actually using 2 layers of circuits. So one layer is, as I mentioned, you have EVM circuit, RAM circuit, all those EVM-specific logic circuit. and you will result in multiple proofs, right? You definitely don't want to verify multiple proofs on chain through one verifier. So what we do is that we build another aggregation layer to aggregate multiple proofs into one proof, so further reduce the on-chain verification cost. And so the first layer need to be really expressive because it needs to express the EVM logic, the RAM circuit, all those like your real computation circuit. And the second layer need to be really verify efficient because you need to verify the proof on EVM. And so let's take an EVM circuit as an example. So for the trace table, EVM circuit has over 100 columns and over 2,000 custom gates and 50 lookup tables. And for around 1 million gas, it needs 2 powers, like 18 rows. And if you double the gas, then you double the rows. So it's so you can imagine like wide table, and that's for EVM logic. And for the aggregation circuit, you have like 23 columns, 1 custom gate, and 7 lookup tables. Because you want this table to be really thin and maybe longer, because it's done like making your table longer than to increase the verification time, but making that thinner will reduce your verification cost. And so for aggregating for circuit, it needs around like 2 powers 25 rows. So this is like your circuit layout, what your circuit layout look like. And then let's take a look at some real number. So the CPU prover is definitely terrible because it's just large circuits. And so what we do is that we build some GPU prover, and we have done a bunch of optimizations to our GPU prover to make that really product level and make sense in practice. So firstly, we build some multi-exponentiation, FFT, and some quotient kernels on GPU to handle the most computational heavy part in prover. And also we pipeline and overlap the CPU and GPU prover to make that another like 2 times faster. And also we have a multi-GPU card implementation, like one CPU with 4 GPU cards, you can efficiently utilize multiple GPU cards, and also a bunch of memory optimizations. And the performance improvement is significant. So for EVM circuit, the GPU prover only takes around like 30 times. It's almost 10 times speed up compared with CPU prover. And for the aggregation circuit, it takes around like 2 or 3 minutes. It's almost like 15 speed up. And so overall, like if you want to finalize 1 million gas, the first layer will take 2 minutes because it needs to compute all those circuits, generate proof for all those circuits, and second layer takes around 3 minutes. So when you need to finalize 1 million gas, it takes around 5 minutes. And if you want to settle down, for example, 10 million, then you just need to make that 20 minutes. But the second layer will be the same. So it's not that bad, right? Like because you have GPU prover, you can wait for a reasonable time to get that finalized. Now, finally, I want to talk about some interesting challenges. Maybe not challenges, but just something interesting like we met when we were building our zKEVM, because we know people are from academia or industry, and maybe you can get some motivation for your next paper. And so from a circuit side, there is randomness. So what does this mean? So think of the EVM, the execution trace table, and think of EVM word. So EVM word makes it really hard to build a circuit because EVM word size is 256 bit. And your native field for the proof is prime. So this non-native match makes that really terrible because you need to do ring check everywhere. You need to carry this very large word everywhere. So what we do is that we break this EVM word into 32 limbs so that you can easily use some lookup to check this 8-bit is 8-bit. And so you decompose that into 32 chunks. But you definitely don't want to carry this everywhere. When you are doing all the operations, it's all this long. So what we do is that we use some random linear combination to compress one EVM word into just one encoded RLC value using this random theta, and AI is just 8-bit. And then you use it everywhere when you are using this EVM word. It's just encoded. Now the problem becomes, how do we derive this theta? Because this theta should be computed after A0 to A31 is fixed, right? Because it's if everything is a witness, then you can just do random things and make some be dishonest for your RLC value. So what we do is that you need to implement some multi-phase prover where you do some partial synthesize for first 32 columns, and then you derive your randomness from the committed value, committed 32 columns, and then use that combine again and do the rest of the witness generation. So, but this makes your prover performance even bad, and especially if we have multiple circuits, the synchronous for the randomness become really problematic. And also another thing to mention is that RLC is not only used for this compressing EVM word. It's also used for encoding dynamic length of input, right? Because your catch-up maybe have megabytes input, and then you can just use one value after linear combine that into one value. Use this one value to represent your input everywhere. And also you can do some lookup layout optimization. But due to this performance loss, we are thinking of just removing this. And we can just use two leaves to represent EVM word after range check. And for dynamic thing, we can just chunk that into fixed chunk and do that dynamic times. So if there are some better way to handle this, randomness and better derive this randomness, maybe we can just use all those optimizations there. But we don't know like which is better. So this is some interesting problems like appear in ZKEVM. And another thing like interesting thing is that the circuit layout. In circuit layout, so many people came to ask like why we need so many like over 2,000 custom gates instead of, for example, the vanilla Plonk just use one gate and you just do that repeatedly for add or multiplication. And the reason why we need so many custom gates is that the execution trace is dynamic. So for example, for step 3, this execution trace, step 3 need to constrain add. But maybe for another execution trace, it need to constrain something else. And the constraint will be different. If you are reusing the standard gates, the varying between those gates will be complicated. And the permutation won't be fixed ahead of time, right? Because if you are proving some, for example, fixed hash function, you know like which gate connect to which gate. Your permutation will be fixed and pre-processed. But this permutation is not fixed. It's just very hard to vary standard gates. So that's the reason why we use like over 2,000 custom gates and different rotations to access cells. For example, like when we execute step 3 and move to step 4, we need to use rotation to prove that those two rows have this relationship. And maybe there are some better way to lay out and reuse some circuit IR to make that more efficient. But this is also like another interesting problem. And another interesting problem is that from prover side, there is both hardware and the proving algorithm. So as I mentioned, like we have 2-layer of circuit and we have GPU prover. And our GPU prover can actually make FFT and multi-exponentiation really, really fast. It's almost not the biggest bottleneck in our prover now. But then the bottleneck moved to witness generation and some data copy between CPU and GPU. So for example, like your witness generation, like no one really cares because it only takes maybe 5% or 10% of the proving time. But if you make the rest of 90% of the time like 20 times faster, then it takes half of the time. And it's really hard to parallel because witness generation depends on a concrete application and it's application specific. So that's the reason why like it's really hard to parallelize this part, and it's actually a real bottleneck for our aggregation circuit. Like our aggregation circuit takes like 3 minutes to generate proof, but half of the proving time is spent on witness generation, and also some data copy between CPU and GPU. And also like for running large circuit, we need very large CPU memory, over 500 gigabytes, which is just very hard for people to run on laptop or normal setup to run this prover. And so maybe there are some better like hardware-friendly prover, and you could design software and hardware for a proving algorithm. By saying hardware-friendly, I mean parallelizable and low peak memory. And also you shouldn't forget witness generation. And we want to enable like the prover running on cheap machines and become more decentralized. Like, more people can run our prover. So maybe there's something to do there. And then for another thing for prover is that the aggregation. So as I mentioned, like there are 2 layers. The first layer to be really expressive. So it needs to express the EVM circuits. So the circuit animation is not only R1CS or like vanilla Plonk. So we want to enable custom gate and lookup support. So that's why like maybe HyperPlonk or some other way like you can support this easily is really important because you want the first layer to be really expressive and also hardware friendly, and also the verification circuit should be small enough for aggregation. And the second layer needs to be verifier friendly because your proof need to be verified on EVM. So it means spot proof and low gas cost. And also prove the previous circuit more efficiently. So maybe there are some better way to compose different proof systems. And some candidates for the first layer, maybe Plonky2, Starkey, Halo2, like some new IOP without FFT, which can make your prover faster and linear time prover. And second layer, maybe Grow16 and Plonk with very few columns and use Flonk or Catch-Fry as their polynomial commitment scheme. And maybe there are some ways, but just incentivize people to think. And last thing is that because we are building some product, it's not some academic prototype, so we really care about the audit and the soundness. Like I take a screenshot from Vitalik, ZKEVM has over 30K line of circuit code, which is really complicated to audit, and it's not going to be bug-free for a long time. So what's the best way to audit the ZKEVM circuit? And also because I know there are some literature and using some formal methods, SMT solver to audit the static circuits, but how you audit a virtual machine circuit based on some IR? For now we are doing audit manually, and also we do some in collaboration with some company doing formalification for some opcodes. But if there are some way to automatically audit this, and also reason about the security for the whole system, for example we introduce randomness and whether it will influence the soundness. And also, like, we need to prevent the case, in case if we're really missing some constraints, what will happen, and what's the bad things that attacker can do. And maybe we can just, maybe submit 2 conflict proofs and halt the whole system and something like that. And just, quick summarize, like, circuit can be improved, prover can be improved, secure can be improved, a lot of things can be done, like, in both academia and industry, and hope more people can join this, like, process. And I think that's all for today, and thank you.
Thank you. I think we have time for one short question. So do we have any questions from the audience? Yeah. Well, I actually have one small question. So the numbers you're showing, is that for one smart contract execution with 1 million gas?
Like arbitrary, like at Friday it's 1 million gas.
Okay, I see. So
by the slot and,
I see.
Like how many steps you need.
I see. Yeah. Thank you. Okay, then I think we are going to take a short break of 10 minutes, and then we are going to see everyone back at 2:20.
Okay, great. So welcome to the afternoon to this session. So we're going to start with the first talk by Howard from Alio. Everyone, please sit down. We're going to start the next talk by Howard Wu. He's from Alio, and he's going to tell us about demystifying ZK programming.
Hi. I'm Howard. I'm a co-founder and CTO of Alio, and today I'm going to be talking about how to build a programming model that supports zero-knowledge applications on an L1. Before I begin, I just want to say that this talk is based on this paper called ZKEVM, which was published at Oakland 2020. And for those who haven't, you should check it out. The introduction is very approachable, and it helps to motivate both the scaling problem and the privacy problem, which I'm going to be covering today. So to get started, on a high level, I think it's become clear that decentralized applications are growing in terms of use cases. There's many categories where this type of a ledger is very useful. But one of the big challenges is that they have some major limitations. And to even talk about what the limitations are, let me start by just going through how a decentralized ledger works. Typically, it works through this operation of re-execution. What I mean by re-execution is that users broadcast a transaction, which contains in it the application, some input and a signature to authorize it. The user broadcasts this to a network. The network checks by re-executing this computation in this application. If it's valid, then they will update the state associated with that. This seems fairly reasonable, so what are the problems? Well, the first is that this model of re-execution hurts scalability, and to give you concretely what I mean by that, each party re-executing is a huge cost to the actual system. To give you some numbers to put it into perspective, if you look at, say, ETH1 with 3,000 nodes on the network, if you have about 5 seconds worth of computation in a block, and remember on Ethereum there's a new block every 13 seconds, if you just have 5 seconds worth of computations, that adds up to 15,000 seconds of work that's re-executed every block. In human terms, that's about 4 hours of work for every 13 seconds of block time. In short, this is very wasteful. I think the second point to call out is that ledger re-executions hurt privacy. And what I mean by that is that the core strength of a ledger today is also its primary weakness, that you can see who the sender is, who the receiver is, what the inputs are, what the outputs are, and what program it was that was executed. And just by this sheer knowledge, you learn a lot about a person, you learn a lot about someone. And the example that I like to give is that it also, from a Web3 perspective, breaks the UI UX you would expect on the web traditionally. Like in Web 2, if I have a bank account and I want to send money to you, you'd send me your bank account number, and knowing your bank account number doesn't reveal to me how much money you have, how much money you earn, how much money you spend. It doesn't tell me where you spend, how frequently you spend, how much you spend. I don't learn any of these details, but if you gave me your Ethereum address, of course I would learn all of these things. And I think one of the bigger implications is that by receiving your address, I'm also opting into being able to track your account for the rest of time. And so there's kind of major implications with the design choice that's being made in L1s today. And so the purpose of this is really to provide and introduce a new type of system, which we call Alio. Alio itself stands for Autonomous Ledger Executions Off-Chain. What it is it's a decentralized ledger that allows users to execute programs off-chain and finalize state on-chain. What it provides in terms of properties is, one, scalability, so it supports thousands of transactions within a block. It also offers privacy, meaning that the transactions reveal no user data about the executed program. And lastly, the transactions are succinct. And what I mean by that here is that it's about a kilobyte in size, and it's fast to verify, less than 50 milliseconds to check. In terms of what applications receive in terms of properties, well, programs can be user-defined. They're isolated in sandboxes, meaning that malicious programs don't interfere with honest ones. And there is an IPC process, so you can inter-process communicate between different programs. So to start by kind of introducing how this works, let me start by introducing the account model, and then let's lift ourselves into this concept of quote-unquote private smart contracts. So just to refresh everybody, in the account model, you have a decentralized ledger that tracks global state. The way it works is that a user will submit a transaction. The transaction contains in it the contract address, some value, some data, a fee, and typically a signature to authorize the spend. Once that transaction is included in a block, every node on the network will update global state by pulling up this account, performing the set operations, and updating the balance and the storage into the new state. There's a few properties with this. The first is that, well, the nice thing about this design is it's very simple. What I mean is that it's very easy for developers to write logic that allows for coordination amongst multiple parties. But the trade-off, of course, with this model, as we talked about, is that re-execution comes with a big burden. It can create queues in the mempool of unconfirmed transactions, which then results in, well, fee spikes in the network. And of course, as we've already talked about, there is no privacy in this model, and this is a big trade-off that's being made in this design. So let's take this model that we're familiar with, the account model, and extend it to support private smart contracts. And naturally, the strawman construction would be to say, why don't we start by committing to the value that's going to be put in the transaction? Why don't we encrypt the data that's going to be broadcast over the network? And instead of purely signatures, let's use proofs so that we can actually perform a proof about the state transition that's being made. So it's a predicate that you're expressing to perform this state transition. And on chain, why don't we change the account model from storing your balance in the clear to a commitment of the balance? Let's take that piece of code, let's turn it into a predicate so that you can be reasoned in a proof system. And lastly, with storage, let's encrypt that storage under the contract address. When you put it together, it looks something like this, meaning that you have transactions now with committed values and encrypted data, and the balances and storage are also committed and encrypted to respectfully on-chain. In terms of what the proof could do then, the first thing that we would want to say is performing a state transition like this, you would want to take the existing balance and the existing storage, and you'd want to produce a claim that there exists a new balance and a new piece of storage for that account via the state transition. And what the state transition will check on a very high level is that the first thing is you want to check that value is conserved. So you want to basically do a value balance commitment a check to make sure that the old balance sums up to the new balance and you're not minting money out of thin air. The second thing that you'd also want to check is that the predicate itself is satisfied. And what I mean by that is you want to take that piece of code that exists in the contract as a predicate form. You want to pass into it all public information, which is the committed and encrypted values. And then you want to open the commitments and the encryption as private inputs to that piece of code. And you proceed to execute that in order to show the validity of your state transition. Now, this model seems very nice. Let me just say this doesn't work. And let me say why this doesn't work. The first thing is to say concurrency is broken in this. And what do I mean by that? Well, say user 1 comes and says, I want to update program A with transaction 1. The problem is that when user 2 comes, they're going to be producing a proof of a state transition on outdated state. Why? Well, if you remember, we were saying that you're going to pass in the existing state, you're going to perform a state transition on it, and then you're going to push out the new state. So when you think about it from, say, an ERC20 contract today has a mapping of every address with their associated balances. And what I'm doing is I'm consuming that entire state. I'm showing for everybody who's not the receiver of this transfer that their values are exactly identical to before. And then I'm performing a decrement on my account and an increment on the receiver's account and showing that via this state transition. Now, the problem with that is, of course, it's very wasteful. It's also growing in size, which is not easy for snarks to reason about, and it's also not efficient. And so, from this model, concurrency itself has a fundamental challenge. The second issue is that we haven't remedied the full privacy guarantees of this model. What I mean by that is when this address goes and performs a call to a contract, even though the data is hidden, it's very clear if I know your address, I can still learn that you are using this address, and I can see every time you're using this contract. I can see not only the specific contract you're using, but also the method. And this is in part because of the way that the account model itself is represented. Remember, the account model is indexed by your address, and so it's a fundamental requirement of the account model design to have your address be the kind of key in the key value pair. And so because of this, you get some privacy, but you don't get the full spectrum. And let's just walk through the properties. The first thing is that this design, of course, as we just said, has no more ledger executions. And the reason for that is that we're using ZKPs to effectively perform the state transition off-chain, and thereby increasing the scalability so long as the proofs themselves are succinct. Next, of course, we're getting data privacy because we're committing to the balance and we're encrypting that type of state on-chain. And so there is some notion of data privacy on-chain. But there is no account privacy because, again, the address itself can't be encrypted. The ledger and the triad that stores it relies on it in order to index into your leaf. And so, from that perspective, if I know your address, I know how frequently you're transacting, I know what time you're transacting, I know what currency you're transacting with. I can see these types of metadata, and that leakage is not great. Next, of course, one of the kind of main challenges with this is that the predicates have to consume the entire program state in order to update it. And that's not a great model because you're effectively needing to consume, well, everyone's data in order to just update your data. And because of that, well, concurrency doesn't work, as we've already established. And so let's try to fix this. And the way that we approached fixing this was by introducing what we call the record model. The idea of the record model is that you have a decentralized ledger that will track each record via global state. And so under the hood, the way it works is that users will come and broadcast a transaction, which contains within it transitions. These transitions themselves have a few items. They have old records and new records. These old records represent the existing state that was already on-chain, and the new records represent the new state to be updated on-chain. It also, of course, includes a fee to pay for the transaction, as well as proofs to validate the state transition. Once a transaction of this form is admitted on-chain, the way that it's updated is to say the program itself, its ID and its code remains unchanged, but the records themselves have been changed. And so we've kind of issued new records for this program in order for that to be the actual latest state of the chain. And I think one thing that's worth calling out is that in this model, notice that the owner of the record is not the kind of index. It's actually just another parameter within the record. And so because of that, you're now indexing programs by a separate ID that is decorrelated from the actual account address associated. And this creates the kind of abstraction layer of the record that we can now use to introduce concurrency, which I'll show next. And so the first thing that I want to claim is by removing and moving that address down into just an encrypted ciphertext in the record, we can achieve concurrency in this model. And the second thing is that when you consume a record, you will now mint what's called a serial number. And with this serial number, it will allow you to detect double spends. And so each record can only be spent once on a network like this. And every time you spend it, it produces a deterministic serial number that can only be seen and used once on the network. So in terms of what we're changing inside of the predicate to make this work, well, the first thing is that the given is going to be the predicate, the code itself, as well as the old record, so the existing state that you're going to be consuming. The claim is now that you're going to be minting out these new records, which are going to be the new state that you're performing on. And lastly, of course, the first part remains the same, that I'm going to check that the balances are conserved, the value conserved, that we're not minting money out of thin air. And the second part is that we're going to check that the predicate is satisfied. Notice that the statement here is, it's easier now in the sense that we only have to produce for this predicate the state that corresponds with what I own that existed on chain, as well as the state that corresponds to me for what's coming out as part of this new state transition. And in the private inputs, what I'm going to be assigning to it are the openings to this, so the old balance and the old data for the old record, as well as my private key in order to prove that I own these records. And so the predicate checks that my private key corresponds to an address, and the address matches the decrypted address in the record itself. And so this is fundamentally the kind of shift in terms of how you want to architect state. I think one way to kind of reason about this design is also to think through, the account model, but with shards of records within every account. This allows you to then give an abstraction where, say, in your EDC20, for that mapping, everyone's entries in the mapping are records. And so when you go to produce a state update, you're only consuming the records in that map that correspond to your account, as opposed to having to produce a state transition about all of the records in that program. And so this type of an abstraction gives you the ability to now have user A come update their records within this program, have user B come at the same time update their records in the same program, and then have the mempool have consensus effectively take those updates and create the updated Merkle tree and the updated Merkle root associated with that state now. The main intuition is that it's disjoint. And because of that, you end up with a few new properties. So the first thing is that because the address is decoupled from the way you index into global state, you now can achieve account privacy, meaning that when I send money to you, to an alio address, it looks the same as a bank account number, that it doesn't reveal to me what applications you use, how much money you have in the account, what tokens you tend to transact with, what amounts associated, any type of data associated with that. It looks the same as bank account numbers in that sense. The other aspect is to say that because of this disjoint nature of these records, it also now allows you to consume state very efficiently. I don't need to prove the entire program state. I only need to prove my portion of program state that I'm updating within this program. And lastly, of course, because of that, multiple people can interact so long as their records are disjoint. And you'll detect that they're disjoint in the mempool because the serial numbers will duplicate if you're spending and consuming the exact same record at the same time. And so this is what we kind of think of as like the first layer of off-chain concurrency in this model. And the last thing to call out is just like in terms of on-chain concurrency, we work in a very similar manner that you can introduce on-chain executions whereby from the mempool layer, you can then order these records to be executed in a specific sequence so that you can actually create kind of two layers of concurrency in this model. I think that it opens the doors to a lot more flexibility in terms of user design and certainly in terms of application expressivity. To give you kind of one concrete example of this, because of this kind of model of executions off-chain, I can then, for example, play a game of poker where I, as the dealer, can deal to 9 players their cards and then do a round of check or bet where every player is performing their state transition executions locally, and they're iteratively performing check or bet, check or bet, check or bet. You can take these transactions, put them into one transaction, and broadcast that on-chain. And so it gives you more real-time interactivity in a model like this. The last pieces I want to get to are really to talk about that the model that we have in terms of building this is it's really a mix of many disciplines, and in order to build a system like this that's performant, it actually requires many disciplines and many subfields to actually be very practical for computers today to actually perform it. And your weakest link is any piece here that's slow, really. And so the way that we ended up architecting our solution was really by designing some elliptic curves here. The first one that we sampled was BLS 12377. We chose this curve because it is pairing friendly, so it enables fast proof verification. The second curve here is we extended BLS 12 into a twisted Edwards curve. And the twisted Edwards curve is very nice because it allows for efficient cryptographic primitives to be executed on it. In terms of the proof system that we use Marlin, which was published in Eurocrypt 2020, and we instantiate Marlin on BLS 12377 to produce statements for predicates that are executed on Edwards BLS 12. The reason that we chose Marlin is that it has a universal setup, and so the nice thing about this design is that as a developer, when you deploy, you don't need to worry about setup ceremonies or trusted setups in general. You can use this universal setup in order to instantiate your program and deploy it immediately to chain. In terms of the way that programs are architected because of this model is that we've broken up the abstraction into 3 layers. There's Leo code, which is a high-level programming language that looks and feels a lot like JavaScript, TypeScript, or Rust. And it compiles down into what we call ALIO instructions. ALIO instructions are assembly-like, and the rationale for the ZK folks that like to count constraints is that in this assembly level, every opcode itself is a circuit. And so you can also, instead of going the Leo route, if you care a lot about the constraint counts, you can kind of hand wire circuits by composing opcodes in order to get to the most granular sense of your constraint costs. And then underneath that is that we serialize it into AVM bytecode. And one important point to call out in this design is that between ALIO instructions and AVM bytecode, there's a bijective mapping, so I can transform AVM bytecode into ALIO instructions and vice versa. I think that this helps a lot with the user experience, especially within crypto. When you think about, like, from the Etherscan perspective, if I want to see what's deployed on chain, this gives a very clear semantic on the instruction set that's being used, and I can at least start to immediately deduce what's happening there. Some teams have already started experimenting with disassemblers and decompilers to take ALIO instructions and bring it back and lift it into Leo, and that lifting also then gives even more semantics. Obviously the trade-off of lifting it is that you do lose some variable names, and so you do end up having to deduce kind of and interpolate what's happening, but nonetheless it gives a far greater sense of usability to what is deployed on a network this way. To give you a concrete example of what this model looks like, here's an example of Leo code. We have here a program that's just hello.alio. Once this is deployed, there's a function here that happens to be called main. And with this main function, we have two types of inputs. There's a public input x and a private input y. In this particular operation, we're going to multiply x and y into z. And so you have let z equal to x times y, and we're going to return z. When we compile that down, this is what it looks like in ALIO instructions. You have function main again. You now have two inputs. Notice that x and y have been lost. You now have register 0 and register 1. So now you have register 0 as a public register and register 1 as a private register. We're again multiplying x times y equals to z, so you have a mul operation, which mulls R0 and R1 into R2. And then lastly, we output R2, which is z, as a U64, and we had denoted as a private variable. And of course, it should be no surprise when you compile it down to AVM bytecode from there, it looks like hexadecimal. So this is kind of the rough outline on that. Given the time constraints, I want to call out a few things. The first thing is that ALIO is proudly written in Rust, about 65,000 lines of code and 40 plus contributors. It's fully open source. You can find the code on GitHub at github.com/AlioHQ. Testnet 3 is currently live, so for those who are interested to play around with what I just presented, you're welcome to do that. The repo that I recommend you check out is this repo, github.com/AlioHQ/workshop. In it, you'll find an install script and instructions in the README to also get syntax highlighters in your IDE. We support VS Code, IntelliJ, Sublime, and it'll let you immediately start playing around with applications. In here, there's 6 examples. A few to name some are auctions. There's Battleship, there's Tic-Tac-Toe, there's a bank, there's a voting contract, and a basic token as well to show you public tokens and private tokens, and public to private tokens and private to public tokens. And lastly, of course, we're on Twitter and Discord. And with that, I'll conclude. I think my time is up, and just want to say thank you very much.
Quick questions?
So who is supposed to compute the ZK proofs in the,
Great
in the model?
question. Yeah. Great question. So in this model, it's an off-chain computation. The user computes it themselves. We also support private delegation of these proofs, and so you can pick third parties to also compute that for you. The nice thing about that model is delegating to a third party, of course, entails producing a proof, and so you'll immediately know if they're being dishonest with that delegated work. And so this model does not do on-chain proving. It is merely for checkpointing and storing on-chain state then.
Is there a security privacy issue if the proof is being delegated?
Great question. So in the current model, we assume that the delegator learns the information. The work that Pratyush and I have been doing is also to basically take this and move that so that you can perform part of the computation in the proof system off-chain, so that when you send it to the third party, it's fully private then.
Hi, Mike Smith from Bit Rainforest. My question is, our team of developers have already developed a few apps, and we'd like to know what are the reward rules for phase 1 of the...
Great question. So for those who are unfamiliar, there's 3 phases to testnet 3. The first phase is writing programs, and we've open sourced this part here. To be frank, we're going to be posting a leaderboard on the Explorer that will allow folks to basically upvote and downvote. We're also going to be hand curating these ourselves, and there's going to be 2 different types of categories for rewards. The first type is going to be based on popularity metrics of that leaderboard. The second type is going to be based on ourselves and the grants team handpicking ones that are interesting, that are foundational and also application driven. Those are going to be announced as we kind of roll this out. Phase 2 will also be coming soon. This is for provers who are interested. We do have a coin-based puzzle. It is basically a way to grind ZKPs, and in the process, Consensus will incentivize provers to kind of develop specialized hardware with that via incentives paid out from chain. And of course, the third phase will be us moving into the full BFT, where it supports anyone staking on a network like this. But yeah, thank you for asking.
I think we're running a little short on time. Okay. Maybe we can take it offline. Yeah. Great. Thanks.
All right.
Thanks a lot.
Thank you very much. Yep.
Okay. For the next talk, we have Jeremy Brutzel, and he'll talk about risk zero.
Hello, everyone. Hi, my name is Jeremy. I am from Risk Zero, and today I want to talk to you a little bit about the zKEVM we are making, which is a general purpose zKEVM. And wait, hold on. This is the clicker. Yes, great. Cool. And do we have a laser pointer? Oh. Yes, great. Okay, cool. So what is Risk Zero? So it is a open source Apache 2 licensed zKEVM, which includes both a prover and a verifier. It is implemented based on ZK Stark's proof system, and what it does is it emulates the execution of a RISC-V processor ISA. For people who aren't familiar with RISC-V, certainly you doubtless know that processors in modern computers, include like x86 is Intel's processor. Your phone probably has an ARM processor in it. RISC-V is another processor architecture that is fairly popular and is both very simple and is also completely open. So we use that as the basis for this zKEVM. So I want to talk about how people develop zero-knowledge proofs and what the development flow works like. So the question is, if I'm a programmer and I want to, for example, prove something like I own this many Bitcoins or whatever it is, right? How do I do that? Well, one mechanism is to actually use a circuit-based system where I actually build an arithmetic circuit. I make a bunch of constraints in some finite field, using polynomials. And there are mechanisms to help make that easier, such as circuit compilers, Circom. In fact, Alio, for example, has a very sophisticated circuit compiler. And so that's sort of one way to do it. The other way would be to have a zKEVM that uses its own architecture internally. This is what like Cairo, for example, uses, where you have a virtual machine that executes sort of individual instructions, but that architecture is specifically optimized to run inside of a zero-knowledge proof system. Both of those two methods require, sort of custom development. They require you to write your program specifically for the zero-knowledge proof system that you're using. On the other hand, you have sort of these ones that try to leverage existing architectures or programming languages to make it easier for a programmer to run existing code inside of a zero-knowledge proof system. So the work on, sort of zKEVMs, which a number of people are working on now, is to allow you to run Solidity or general EVM code inside of a zero-knowledge proof system. We're focusing specifically on a zero-knowledge virtual machine that allows us to run existing ordinary code in C++, Rust, or sort of any kind of, existing language that compiles down to machine code. So why did we pick RISC-V as the processor architecture to make the VM? We could have done, Intel, x86 or ARM, and largely it's because the RISC-V processor architecture is extremely simplistic. There are only, for the smallest version of it, you only need to implement 40 opcodes. It's very modern. It's fully deterministic. There are descriptions of exactly what should occur at every step. There's no undefined behavior. There's even formal verification suites for the whole thing. And it's also very well supported by existing tool chains. You know, the standard Rust, you know, compiler can compile down to, you know, RISC-V as, you know, you can get a version of Clang to compile normal C++ code down. All of this is already done. LLVM fully supports it. And it also has a lot of extensibility. So if I wanted to add a custom instruction to do something special, there's a very well-designed way to do that. And interestingly, it's designed for efficient hardware implementation. And, you know, of course, we're not implementing it in hardware. We're implementing it instead of in circuits, like gates, you know, with digital logic. We're actually implementing it in terms of arithmetic circuits using polynomial constraints. But surprisingly, those two systems mirror each other enough that many of the decisions in the design of the RISC-V ISA that were designed to make it efficient to implement in hardware turn out to actually be helpful to make it efficient to implement in terms of a zero-knowledge circuit. So just in terms of describing kind of what the workflow looks like for a programmer in the system, you know, basically the idea is you would have some sort of code. And what's cool is not only is there code that you've written in C++, but you can also take advantage of existing libraries or the huge ecosystem that all these systems come with, right? If I want to do a zero-knowledge proof that shows that I decoded this, you know, GIF file and then modified it and then re-encoded it, you know, I want to have a library that can read a GIF or a JPEG. I can literally just import it, and it'll actually run inside the zero-knowledge circuit, right? So these libraries are really cool. You basically compile it with a normal compiler. Most of those compilers internally use LLVM as their back-end representation as a way to represent the code before it gets converted to a particular instruction set architecture. And you can get them to emit a RISC-V ELF file, which is a type of a binary format that, you know, Linux and a number of other operating systems use. And basically, all of this part is all totally standard. We've done nothing whatsoever here. So we start right here. We actually have a way to take those RISC-V ELF files and take those as input to our zero-knowledge proof system, along with some user data, and basically produce a proof. And one of the things with the proof is that, of course, when you're proving something, you want to attest to something being true. And so the way that's represented to the user is that they write something to the journal, and the journal is the public portion that ends up in the resulting proof that allows, and so whatever you want to attest, you write into the journal. And then additionally, given that some developer has done this, the ELF file effectively represents what the program does. So we have a mechanism that turns that into what's called a method ID. A method ID is a small sort of, it's like a cryptographic hash in some sense of the original program. So this represents what the program itself is. And then the verifier, which runs succinctly, can take the proof and the function that was used to make it and verify it. So at a high level. So I wanted to point out an actual real-world example of someone using this, and I actually wanted to pick something that we didn't write. So this is just someone else's code that they ran to use our proof system, and basically someone wrote some code to verify that a Sudoku puzzle is correct. It's actually part of a sort of a shootout among different compilers in terms of trying out different zero-knowledge proof systems to see how easy they are to program in and also how fast they run. So this is actually the code that runs inside the zero-knowledge proof system. So you can see this is just ordinary Rust code, right? And it's actually, I think, quite readable. And in fact, this is sort of how the end user talks to the proof system. There's a special environment that we define. They can read data. And by the way, this is all zero knowledge. So this information is in fact hidden, although I end up committing to it anyway. And then basically you can run some code like here. This actually verifies the Sudoku meets the criteria of a Sudoku puzzle. And what's interesting is we've defined panic so that if you panic inside of the Rust, it executes an illegal instruction. Illegal instructions are not allowable by the set of constraints. And so thus, if you panic, it is impossible to produce a proof of whatever you're doing. So this basically, by the fact that this made it to the end and committed to this hash, we know that, in fact, the thing that is in the journal is, in fact, a valid solution to a Sudoku puzzle. Of course, This particular code, by the way, does not hide part of the puzzle like it would need to, because generally what you want to do is you want to show that you can, know the answer to Sudoku puzzle without revealing it. But anyway, that's just sort of the way they wrote it. But I just wanted to show this because I think it sort of shows how straightforward it is to write software. And I think one of the important things is the ability to import existing code bases in. So that, by the way, is all totally working. You can go to our existing repo. There's a working version of the prover. There's a working version of the verifier. I want to talk a little bit more for the rest of the talk really quickly about what we're currently working on in our private repo, which we intend to also open source fairly, probably toward the end of the year. So one question is, one important factor for zero-knowledge proofs in terms of scaling is the ability to do recursion. And that's effectively to run a verification of a zero-knowledge proof inside another proof. So here's a question. Our verifier is written in Rust, so what if we just run the verifier, compile it down to RISC-V, run it, right? Should work. So the unfortunate thing is that if we were to do that naively, recursion, or just generally verification, requires a lot of hashing, SHA-256 in our case, and finite field operations, neither of which RISC-V is particularly good at. And if you try to naively implement recursion by effectively running the verifier directly, you run out of cycles. The proof system sort of has a maximal number of cycles it allows. However, we have now fixed that, at least in our private branch. We have that should be SHA-256. We have a SHA-256 accelerator, which basically allows you to quickly do SHA-256s inside the proof system, as well as a sort of a finite field processing unit that sort of sits alongside this logical RISC-V processor to do finite field operations. And with those two things, we can now run a verifier inside the proof system in about 1.5 million cycles of RISC-V execution, which is within the realm of actually usable for recursion. And in fact, actually, speaking of that, I wanted to kind of, I'm just going to check my timer here. I wanted to kind of discuss sort of what the overall, so once you have the capacity to do recursion, one of the questions is, how can we do very long running programs? And when I talk about very long running programs, I want to be able to, for example, literally run a copy of GCC inside the proof system and show that, for example, this source code compiles down to this binary and produce the hashes in them both. Or I want to run, some machine learning neural network. I want to, run, MNIST or something and verify that that works. Or I want to, for example, run an existing EVM implementation like Geth and verify, that some, EVM is correct. So we want to be able to run arbitrarily long computations. And so what we're working, once you have recursion, there are ways to do that are less slow than just running the whole thing inside the proof system, because the proof system is general purpose. You could continue to sort of extend the number of cycles the proof system runs over to run very large programs. But instead, we use this mechanism, which actually, the Scroll talk earlier, they use a similar mechanism right internally, which is basically what we call continuations. And the idea here is that you take and you Merkleize the system state so that the state of both the memory and the internal processor registers at any moment in time can be written to a Merkle tree. And then what you do is you make your proofs verify that if you begin in state X and you run for Y cycles, you end up in state Y, right? Or n cycles maybe. So basically the idea is that you show that you can go, you can move from state 0 to state 1 via valid RISC-V semantics. And then you can pre-compute effectively the execution of your RISC-V processor outside of the proof system. And so this is just running a normal RISC-V emulation. So this can be done a bit, very, very, very fast. And then what you can do is you can time slice those into points, and for each section, you can then verify that, yes, in fact, if you start in this state, you end in this state. And if you start in this state, you end in this state. And then you can use recursion to verify this proof and verify this proof, which implies that if you start here, you end here. And so by doing that recursively, you can effectively generate a single execution trace that, or a single proof that is succinctly verifiable that verifies the execution of a very long-running program, right? And what's interesting about this is that actually the proving process is parallelizable. So you can actually run a very large program very quickly if you're willing to throw enough computing power at the problem to do so. So I wanted to talk about performance because I think this is really critical. I mean, one of our major interests in doing this, and part of the reason that we chose this entire approach of using sort of an existing ISA, is to make it really easy for ordinary programmers who are used to just writing ordinary programs to be able to write zero-knowledge proofs. And in order to make that feasible, the performance numbers have to be to the point where you can run meaningfully large programs. So on our current open source implementation, this is how fast our imaginary virtual processor runs, about 10,000 instructions per second, which is, not fantastic, but you can actually do useful things. You can certainly run a Sudoku puzzle in that. On the private branch, we've made it significantly faster on the CPU. Now, we're currently working on a GPU version of all of this, which we have we've moved about half of the computationally complex components into the GPU version. Most of them we've experienced about over a 10x speed up in terms of execution time. So, and we also have a number of other sort of straightforward efficiency improvements that we're making. So our current sort of end of year target is to get to around 500,000 instructions per second, so a little under 1 megahertz of an imaginary processor, which begins to start opening up a lot of real, very interesting applications in terms of the sort of use cases. And by the way, if you noticed earlier, recursion is 1.5 million cycles. That would put our recursion times at about 3 seconds or so. So we believe that our goal is to sort of continue this work to get this down to the point where it's eminently practical. And that's my talk. So, questions?
How does RISC-0 compare to Cartesi? It sounds very similar to me.
I'm not sure if I'm familiar with Cartesi.
Oh, they run a RISC-V VM to run code kind of the same way and do a zero-knowledge proof. I don't know. I saw them at DEF CON. It sounded very similar.
Okay.
So actually, I'm curious about the comparison to the talks that we saw earlier today. So there was kind of custom implementations of the zKEVM. If you literally just took Geth and you ran it on RISC-0, do you have a sense of presumably it's not going to be competitive with the zKEVMs that are custom made, but what will be the ratio, the performance ratio?
So currently the answer is, so I suspect it would be significantly slower now, particularly due to the fact that there's a lot of elliptic curve operations that are going on, and we also don't have a hardware version of Kekerak currently. So did I say that right? Yeah, Kekerak, thank you. In the existing implementation. That said, we currently have 2 accelerators. We're actually looking at doing a BigInt accelerator and potentially some other cryptographic hashes. With those 2 things, I think that the performance would be reasonable. In fact, one of our partners, however, is actually are working very actively on that, and in fact have a working EVM that does run inside our proof system currently. However, obviously there's a lot of performance to be done on that. So I don't really have any great back of the envelopes to compare.
Okay. Yep.
Great.
Okay, for the final talk in the session, we have Pratyush Mishra, and he'll tell us about Rust ecosystem, ArcWorks.
All right, hi everyone. Really nice to be here. So today I'll be talking about ArcWorks, which is a Rust ecosystem for developing and programming with ZK Snarks. This is the hard work of a bunch of of many, many people, both at Berkeley as well as elsewhere, some of whom are in this room, I think. But anyway, let's get started. Okay, so I'll do a quick recap of snarks. I'm sure most people by now are very familiar with what a snark is. But basically, it's a protocol between a prover and a verifier. The prover has some secret input, and it wants to convince the verifier that it knows that for some function f, that this secret input sort of satisfies that function. Like you can think of f as being a hash, and w as being the pre-image to the hash, and x is the output of the hash, right? So the prover wants to convince the verifier that it knows the pre-image without revealing what the pre-image actually is. Okay? So basically, a snark is a protocol between these two parties where the prover can produce a very short proof, which it can send to the verifier, and the verifier can check this proof succinctly. So in more detail, the properties that we want are zero knowledge, which means that the verifier learns absolutely nothing about the witness, think the pre-image, except that it satisfies the function. And succinctness, which means that the proof size is small and can also be verified in time, which is much less than the time to actually run the function of the computation. Okay? So they're a very interesting primitive, as I'm sure you've heard already today. There's a bunch of applications such as private transactions, scalable and private smart contract systems, decentralized multiplayer games with hidden information, as well as many others, right? There's a bunch of ton of applications which people have deployed or are in the process of deploying, okay? So how do people actually develop these applications, right? What's the process that they undergo to do this, right? So at the highest level of the stack, when it just thinking of your application itself, you first have to decide what the application is, and then you have to express the computations required for that application in the language of the ZK snark. So ZK snarks, they don't understand, maybe now they will with RISC-0, for example, they will understand like Rust or Python or something, but for the past few years, the most efficient ZK snarks that we have, they don't really understand your standard programming languages. So you have to express your problem in a way that's amenable for efficient ZK snarks. Okay, and there's again a bunch of choices at this level, so you're already inundated with a lot of things to think about. Okay, and then once you've done that, once you've figured out, okay, this is the language I want to use, or this is the framework I want to use, now you have to figure out, okay, what ZK snark should I use, right? And again, now there's a bunch of choices to make here, right? There's Graph16, for example, the many variants of Plonk, the many variants of Starks, and so on. So there's like a bunch of, like a very large decision space here. Okay, so okay, let's say you've done that, you've made your choice there. Now you still have to sort of choose the underlying algebraic object which you will base your snark on. So this includes choosing things like what kind of finite field you want to express your constraints over. If you're going for a pairing-friendly system, what kind of pairing-friendly curve? If you're not, then what kind of sort of standard curve? Basically a lot of choices again at this level. And finally, you're still not done. You actually have to sit down and implement and optimize your algebraic object, right? So this involves, again, a lot of deep knowledge of very applied cryptography, such as implementing fast pairings, specialized group arithmetic, and so on. Okay, so this is a lot of work. If you put together all the things that you have to do on the slide, it's a lot of work. And ideally, we would like to sort of avoid having to repeat the work over and over and over again. Okay, so as a result of this, people have developed, over the past few years, many libraries for ZK snarks or frameworks for ZK snarks, right? But the problem is that sort of each of these frameworks and libraries, they don't really share a lot of common infrastructure. So depending on the language you have or what you're writing your constraints in, you end up with a bunch of libraries, for example, in JavaScript or in Go or in C++ or in Rust. Okay. And there are some good reasons for this, right? For example, everybody implements their sort of new optimizations to overcome the overhead that accompanies snarks, right? There's new algorithms and techniques every few months. The space is moving very quickly, so the algorithm you're using today or the proof system you're using today might become obsolete in like a year, right? So, and furthermore, you might have some constraints imposed by your existing code base. So if you're using Go, you might want to use, for example, Gnark to construct your proofs. All right, so there's a lot of valid reasons to do this, but there are also problems which come with sort of re-implementing your snark frameworks every time. So number one, there's a lot of duplicated and wasted re-implementation effort, which means that optimizations are sort of scattered across all of these libraries, like an optimization which exists, for example, in maybe not in LibSnark anymore, but let's say Gnark is not one that is replicated necessarily in Bellman. All right. Furthermore, upgrading becomes difficult. If you're using a particular framework, then it might become difficult. And sort of a new snark comes out, it might be difficult to upgrade to that snark if that framework doesn't implement or support that, right? And we are already seeing this with, for example, a lot of frameworks we use R1CS, but now sort of Plonk-style arithmetizations are becoming popular, and there's like a sort of separation between the two ecosystems. And finally, because of this reimplementation effort, auditing and bug fixing efforts are also sort of split across all of these libraries, right? So a bug which is fixed in one might not necessarily be fixed in another. Okay, so how do we overcome these issues? And the idea is to basically sort of take a very standard software engineering approach by making it very easy and low cost to reuse a library or portions of a library. So we want to design a framework which is modular. It should be easy to mix and match components and reuse stuff from one library and then another, like say, constraint writing framework from another library. Okay, and it should be easy to swap things out as new schemes come up on ePrint, for example. It should be ergonomic. It should be easy to sort of write secure protocols by default. You shouldn't have to be, a very, know the nuances of applied cryptography to implement your protocol securely. And then it should be easy to integrate these into existing code bases. And finally, to get both of these benefits, we shouldn't be sacrificing efficiency, right? Because in the end, efficiency is what matters in snark land. Okay, and so this is basically what we set out to do in ArcWorks. It's a purportedly modular, ergonomic, and efficient Rust ecosystem for ZK snark programming. And over the course of this talk, I'll try to convince you of this. But at a high level, we achieve modularity by leveraging the Rust type system to abstract away details and offer very simple, reusable interfaces that you can use to construct your snark or your application on top of a snark. Okay. From an ergonomics perspective, again, we leverage the type system and Rust's properties to encapsulate implementation details and offer secure defaults, so you're not shooting yourself in the foot if you try to implement your own snark, and also to sort of allow calling these the result of your implementation from other libraries or other languages. Okay. Finally, in terms of efficiency, we implement and offer sort of state-of-the-art assembly or intrinsic implementations of field and curve arithmetic, as well as algorithms on top of these to offer sort of similar to best-in-class performance. All right. So let's quickly go over the stack. So we do this by basically constructing ArcWorks as a sequence of stacks of like related libraries. At the lowest level, we have libraries which implement your algebraic infrastructure, such as finite fields, elliptic curves, polynomial arithmetic, so on. Okay. Above this sort of generic interface offered by these libraries, we implement the actual things you'll be using to develop your application, such as a generic interface for writing constraints, as well as concrete implementations of ZK snarks. Above this interface, we implement standard implementations of popular computations or gadgets, such as Boolean arithmetic, integer arithmetic, as well as cryptographic primitives, such as hash functions, signatures, Merkle trees, and so on. And finally, we also have some actual applications that we've developed on top of this, at the top of the stack, which leverage sort of all of these components down below. All right. Okay. So in this talk, let's go through the levels of the stack one by one, starting with the lowest one, which is the algebraic infrastructure. So for background, basically all snarks require two kinds of arithmetic, usually. They require finite field arithmetic, which is arithmetic modulo a prime, as well as manipulating polynomials over these finite fields, over the integers modulo p. Okay. So this is at the base of basically every snark you've heard of or used, right? Many other snarks, such as the ones that you might have seen today, like Gross16, Malin, Plonk, etc., they also require efficient elliptic curve arithmetic, right? So what we want at this level of the stack is that it should be easy to implement new fields and new curves so that you can experiment with new design choices while having good performance, but you also don't want to replicate effort that's already been done. If somebody's already implemented an efficient and optimized finite field multiplication routine, you shouldn't have to copy that and manually edit it, right? Okay, and that's basically what we get. From the ergonomics perspective, let's take a look at how we would achieve this for the Pareto-Nerig 254 curve, which is, for example, in Ethereum. So to implement an elliptic curve, we have to do a few things. We have to first implement the associated fields, like the scalar field and the base field, and then implement the curve itself, which at least, at the very minimum, requires specifying the curve equation coefficients, specifying the cofactor and generator of the group. So let's take a step through both of these, okay? So in ArcWorks, to implement the fields for BN254, this is all you have to do. It's like these 5 lines of code. You specify the modulus, you specify the multiplicative generator for the field, and then you're done. So this is like your entire curve field implemented. This is for the, I think, the scalar field. I don't remember anymore. But the same thing for the base field. It's just 5 lines of code, and now you have an efficient implementation of both the scalar field arithmetic and the base field arithmetic. Okay. So that makes life easier. What about the curve itself? Again, here it's very simple. You specify what the base field and the scalar field for the curve are. You specify the cofactor. It's the BN254G1 is a prime order curve, so the cofactor is just 1. And then you specify the coefficients. The coefficient in this case is 0, the A coefficient. If you remember, the equation is x cubed plus ax plus b. So A here is 0 and b is 3. And you specify the generator, which is a point on the curve. It's just 1 and 2. So this is all, like those past 2 slides, is all you need to implement the BN254G1 curve, right? Yeah, so this is much better than if you look at, for example, in libsnock, you have, I would say, at least 150 lines of code to implement the same curve. All right. In ArcWorks, we've leveraged this ease of implementation that we've developed to implement a lot of curves that are used in basically every project out there. So if you have a project that's using an elliptic curve, we probably support it. So for example, we implemented BLS12381, BN254, as you just saw, the pasta curves, which are used in Zcash and Mina, BLS12377, and the associated curves, as well as cycles of curves. And now I think in the latest release, we'll have support for curve 25519 and SecP256 and so on. So basically every curve you ever heard of is supported in ArcWorks. Okay. This makes it easy to port your existing system to work with ArcWorks. All right. Okay, so we've not just implement these curves and they offer just like independent interfaces. They all are sort of abstracted behind a common curve interface. And what this allows us to do is to easily switch curves as sort of new curves come onto the scene. So for example, if you're using Grot16 with BN254, right, which was the sort of standard a few years ago, this is how you would instantiate Grot16. But then we learned that there are new attacks on the BN254 curve, which sort of reduces security level. And now you want to upgrade your proof system to use a more secure curve, such as BLS12381. You can do this by just changing one type parameter in your code, and now your system works with BLS12381. Of course, you have to actually migrate your larger system. But from the cryptographic perspective, there's nothing complicated going on. Okay. Same thing from like signatures. You can easily switch out elliptic curves, even non-pairing friendly ones, to support a new curve. All right, okay, so all this ergonomics and modularity is very nice, but does it come at the cost of performance? And thankfully for us, the answer is no. We've done a lot of work to, even in these generic implementations, match or outperform specialized and hard-coded impulse. And I won't go into the details here, because I'm not sure how much time I do have. But basically, in ArcWorks, we're able to achieve performance that is sort of better than hard-coded implementations for BLS12381 and Bellman, and in some cases matching, but oftentimes not much slower than state-of-the-art libraries like MCL, which use techniques like dynamic code generation. Okay, and of course, there's like a lot of room still to go, but yeah, the idea is to not compromise the modularity or the ergonomics while still achieving or improving on this performance. Okay, so that's at the lowest level of the stack. You can get good performance without sacrificing on ergonomics or modularity. At the stack above, what we want here is basically we care again about optimized performance. We don't want to compromise on that. But a couple of other things also come into play, right? If you're implementing a snark, it's already a very complex mathematical object. So when you're implementing it, you want to be able to cross-reference it against the paper or the math. And so your implementation should sort of resemble that as closely as possible, right? That would help with auditing and bug fixing, for example. And finally, should also be easy to compare and benchmark across different proof systems. And what we don't care about at this level are the details of the curves, like what elliptic curve you're using or how constraints are generated. You just accept some constraints and spit out a proof. Okay, so I won't go into all the details of all the properties here, but basically in terms of modularity, which is what helps in comparisons and benchmarks, for example, we have generic snark interfaces, which make it very easy to switch between proof systems, right? So for example, you started your system off with Grok16, which is a snark with trusted setup, circuit-specific trusted setup. But then you heard that circuit-specific trusted setup is bad. So then you decided to switch, I guess you heard that there's this new variant called Grothmiller 17, which offers simulation extractability, which helps a lot in actual deployments. So you can easily switch over our implementation from Groth16 to Grothmiller 17, again, by just changing one type parameter. And then you heard that circuit-specific trusted setup is bad. So you want to switch to something like Marlin or Plonk. You can do that by just changing one type parameter. Basically, sort of this modularity extends throughout the stack. You can switch out your polynomial commitments if you've heard of that, again, very easily to obtain, in the end, a snark with transparent setup. All right, so this modularity is helpful in doing, for example, comparisons and upgrading your system as new improvements are found. But what about the implementation of the snarks themselves, like when you're below the abstraction layer? So here what we want, as I said before, is that the code should match the math. And what you can see here is basically, this is the Groth16 verify, right? It's a relatively simple algorithm if you write it in math. But what we'll see is that this is basically the implementation of that same verifier in ArcWorks, right? And it matches those two lines of math exactly, right? You do some scalar multiplication where you accumulate the sum, and then you do a pairing product between three things. And that's exactly what this is. So by doing this, it's very easy for an auditor or somebody who's trying to fix a bug in the code to sort of cross-reference different implementations, with the paper and so on. Okay, so that sort of wraps up this layer. How much time do I have?
Maybe 2 minutes.
Okay, I'll wrap up quickly. Okay, so finally moving on to the last level of the stack, which is actually application programming. How do you do this? Unfortunately, most of these snarks, they understand, as you might have heard, algebraic constraint systems, so things like R1CS or Plonkish arithmetizations. But programming these is very painful, right? I'm not going to sit down and write R1CS matrices. I'll probably lose my mind. Okay, so what you want is to be able to program in a high-level way, but with still having a lot of control over the efficiency of the proof system, of the resulting constraint system, right? And so there's like a lot of high-level languages that compile down to constraints, but you sort of lose the control over the efficiency of the resulting constraint system. So what we want is to have both good performance, like a small number of constraints, but still high-level constraint writing. So it's not like you're writing the matrices yourselves. Okay, and this is basically what we try to achieve in ArcWorks. Again, so here's Kurosawa multiplication. It's a particular algorithm which is used, for example, to implement finite field extensions. And above is sort of the native implementation, like how you would implement it in Rust, for example. And below is the same code in constraint form. This is in libsnark, right? So it's very difficult to actually match up what's happening above with what's below, right? If there's a bug, it's very difficult to detect. And yeah, you can definitely talk to, for example, Ale. He didn't have a pleasant time programming constraints in this. Okay, so what we try to do in ArcWorks is try to minimize the deviation, and what you can see is the same code, the same algorithm implemented in constraint form in ArcWorks looks almost exactly like the code, the native code, right? So this makes it really easy to catch bugs and debug and audit your implementations. And the cool thing is that the efficiency is the same as what you saw on the previous slide with that big blob of code. Okay, basically that wraps up my discussion of the constraint programming. The question is, okay, has all of this effort actually been useful? And the answer is yes. There's been a lot of impact, both in industry, a lot of companies, some of which are in this room have used it, and also a bunch of folks have used ArcWorks to implement their schemes and compare against existing snarks. This has been the work of a lot of people. I think I haven't updated the slide with the latest list, but yeah, this will keep growing. So thanks to all the contributors. And if you would like to join and participate and develop or work on snark development, please get involved. These are some links. Thank you.
Questions?
I'll say one thing, Petrus, that I just wanted to say thank you for developing this. This has been an amazing tool for pushing zero-knowledge implementations forward. You know, we've built on this, and it's enabled lots of things that we couldn't have done otherwise. So thank you for developing this.
No, it's not just me. There's a lot of people who've developed and contributed a lot to this effort. But yeah, okay, thank you, everyone.
So again, we are going to take a short break of 10 minutes, and we're going to resume at 3:35. Thank you.
People in the back, please, could you take a seat, please? Okay, thanks everyone for being here. We are starting the last session of the day, and we've had really amazing talks, and the last session is also really exciting. So for the last session, we are going to cover some of the more advanced topics in ZKP. So the first one is by Yu Feng, professor from UCSB. Actually, we'll be talking about formal verification in the ZK-land. Great, thank you.
Thank you. Hi, everyone. I'm Yu. I'm a faculty member at UCSB. I'm also a co-founder at Veridice. And I do research in programming language as well as formal method. And today, I'm going to share one of our ongoing work for applying formal method to ZK security. Let's start with the motivations. So the motivation is actually very simple, yet a little bit ironic, in the sense that for those of you who in here, in this room, no matter where you work on L1, L2, or VC or infrastructure, if we ignore the problem of security as well as correctness of your ZK circuits, so all of us is going to end up with working for one single boss, which is going to be the attacker. And so how do we address these problems? So as researchers in formal verifications, I have to say that there's not a single solution or single technique can perfectly solve these problems. So everything essentially boils down to trade-off. So here, x-axis corresponds to automation, degree of automation, whereas y-axis corresponds to assurance. And as the users, you want both metrics to be maximized. And however, there's not a single technique can achieve that. So at Veridice, what we build is essentially we build a set of formal verification toolings that is essentially complement with each other. So how it works from the high level is essentially, let's say you implement a circuit using a domain-specific DSL. So here, your circuit can be written in Circom, Halo 2, NOIR, etc. So we first leverage its corresponding compiler to compile it into intermediate representations, which will be bridged into our KSIR, which is essentially the intermediate representation built at Veridice. And so this is essentially the abstractions in which all of our tooling built on top of it. So including Coda, which is essentially formal verifier that based on interactive theory prover. So in this case, we use COG. And so with Coda, so essentially you can verify a lot of sophisticated like crypto ZK, like protocols, including ZK zero knowledge proof circuits. And the problem is essentially it requires a tons of manual effort in which domain experts need to provide sufficient enough lemma to make the proof proceed. And on the other extreme, so we also have Orca, which essentially leverage fuzzing, and some of you might be familiar with, in the sense that let's say we start from a trace that is accepted by the verifier of a particular ZKP circuit, and then how can we mutate the trace in a way that we can actually fool the prover. And so, and it's turned out to be, it achieved the maximum degrees of automation, but the guarantee that it brings is also going to be much weaker. So in today's work, I'm going to introduce our ongoing work, which is PyCars, a push-button approach that is kind of achieved a good balance between those two matrices. Okay. So before I actually introduce our technique. So essentially, let me set up some basic concepts about ZK. So suppose we want to construct a snark for a particular functions fx. Okay, so in this case, so fx is going to represent encode as a circuit in which it takes a single input x as an input, and then it generates an output fx. And so the circuit is going to compose by a set of components which essentially contain addition modifications over a finite field. So in this case, both input, output, as well as intermediate nodes, we call them signals. Okay, so this piece of circuit is going to compile into an arithmetic representation depending on what the protocol is going to be. So let's say it is going to compile into QAP, quadratic arithmetic program, which is essentially a polynomial field equations that constrain the each signals during the computations. Okay, so and then those polynomial equation will further translate into snark, which is going to contain both prover and verifier. So here, from the verification perspective, we have two code snippets. One is the original circuit, and the other is essentially the polynomial equations on the right-hand side. So what can go wrong here? So you all must be very familiar with this process. What can go wrong here? So here, one of the invariants that we try to enforce is that ideally, the field equation that we construct, and they should produce the same outcomes as the circuit, right? In a sense that they should be equivalent, or at least observably equivalent. So by observably equivalence, what I mean is essentially for every input-output, xz, so in a sense that if running the circuit over the input is going to produce z, so in that case, if and only if x and z satisfy the polynomial equations. And however, based on our real auditing experience, we realize that those two are often not equivalent in the sense that so you might end up with observing that some of the constraint systems from the application domain, they are actually missing some of the range check by the developer. And the reason that people make all this kind of mistake is because manual adding constraint is actually both time consuming as well as error prone. So, and among all of those mistakes they make, so one of the common problem that we observe is essentially so-called under-constrained circuits. So here we call a circuit is under-constrained if the output signal are not uniquely determined by the input signal in its corresponding polynomial form. Okay? And what does this mean and entail? The consequence of the security is that so the attacker can actually leverage this kind of problem to essentially get their bogus proof verify, in the sense that the attacker can essentially claim some output which cannot be possibly produced by the desired FF function that we just saw in the previous slide. And it turned out that the problem of this kind of under constraint is actually the root cause of many vulnerabilities that we have seen in reality, including one of the bugs in Tornado Cache. And the outcome can lead to the attacker to drain all the tokens, and it can also lead to double spending in the sense that the attacker might be allowed to drain more money that he's not allowed to do. Okay, so this is essentially the problem definitions, and so let's dive into a concrete example to illustrate the technique a little bit. Okay, so in this case, let's say we have a buggy implementations on the left-hand side. And in this implementation, I'm trying to implement a circuit which does a none-to-bit functions. And what this none-to-bit function is supposed to do, essentially, it takes an input n, which is essentially a prime element, and then the function is going to convert these prime elements into its corresponding bit representation. So which means that the output is going to be an array with n elements, whereas every element is going to be either 0 or 1. Okay? So this is essentially the spec that we want to implement. And then the detail of the program is pretty standard. And so one of the most interesting part is essentially, so in the middle, the programmer was trying to enforce some kind of constraint with this kind of a triple equal notation. So in this case, this is essentially something specific to Circom in a sense that it's trying to enforce a constraint over every element such that this element is either 0 or 1. Okay, very straightforward. And so the buggy part of the code snippet is actually on the loop header, in the sense that instead of like iterate over m times, the programmers like forget to iterate over the last elements. And what does that mean is that when you compile these circuits to its corresponding arithmetic operations, like equations on the right-hand side, and so what you get is essentially an equations like the following, in the sense that, as you can see, both the first and the second elements of the array was being constrained properly. However, because of the mistake during the loop iterations made by the programmer, and the last elements was not constrained at all. So what does that mean? Meaning that so the attacker can literally pass any value for this for the last element of the output. Okay, and so now we understand the problem as well as the setting. But how do we capture this problem? Okay, so in order to understand that, let's think about that from the humans like intuition's perspective, in a sense that, let's say, as a crypto expert or mathematicians, I want to resolve these problems. What we typically do, essentially, we construct a piece of circuits, and then when we construct a circuit, we're actually trying to do some kind of a reasoning. And for this reasoning, it's going to contain, the first input is going to be the field equation P, as well as a set of signal K that prove to be unique, okay? And then the set is initialized to be empty at the very beginning. So what you want is essentially you perform some kind of rule-based reasoning, in the sense that I have some kind of certain kind of lemma or rule in my mind, and then I try to propagate elements of those kind of elements that prove to be unique. Okay, one example can be, let's say at the very beginning I have the input X as well as the output signal Y, and so let's say I have a rule which is essentially saying that for all the variables that appear on the right-hand side, if they are all uniquely determined, so which means that the variable on the left-hand side will also be uniquely determined. Okay, so in this case, because X is an input and then Z is going to be a linear combination of X, so as a result, Z is also going to be unique. And because Z and X are both unique, and because Y is obtained through a linear combination of X and Z, as a result, Y also going to be unique. So as you can see, through this kind of rule-based reasoning, so we can actually construct a procedure that can try to propagate and then generate this kind of a uniqueness signal until it reaches a fixed point. Okay? In that case, if the output signal happen to be the set that we produce, in this case it's going to be K prime, then we are good to go, in the sense that we already proved that the output signal will also be uniquely determined. And so otherwise, then we have to make the worst case assumption, in a sense that it could be unsafe. So this is essentially the way that we do, like as a domain expert, in this case, like mathematicians or crypto experts. So from the PL or formal method researcher's perspective, what they typically do is essentially they formulate this problem as a query whose answer can be obtained through an off-the-shelf SMT solver. Okay, so let's say right now I want to prove the uniqueness of a particular circuit P. In this case, I can actually form a very simple query, which essentially states that, so can you provide like two different input signal? In this case, it's going to be Y1 and Y2. Okay, they are different. And then can you make those two satisfy the constraint system simultaneously? Okay, so in this case, if the solver is going to give you a satisfiable answer, in this case, a counterexample, then it means that it found an evidence to show that your circuit is not uniquely determined by the input. So as a result, so using the SMT solver, so it can construct a set of K double prime, which essentially prove to be unique, as well as the second set of K unconstrained, which means that all the variable in this set is going to be unconstrained. So which means that based on this answer, if the output signal is going to be in K prime, then we are good to go, in the sense that we prove that the circuit is actually safe with respect to the uniqueness of the output signal. Otherwise, if the output signal is going to contain some signal that is going to have non-empty intersections with the under-constrained variable, then it means that this circuit is actually not safe. So those two approaches sounds pretty like reasonable as well as easy to understand, but they have their corresponding pros and cons. For instance, on the left-hand side, so you can actually encode some domain expert rules, and then which can be done, this kind of reasoning in a very efficient way. For instance, because of most of the circuit can actually, like whose loop actually bounded during compilation time, which means that you can actually run this algorithm in linear time. And it's highly scalable, but it also generates high false positive in the sense that when it gets to a certain scenario in which you cannot apply any predefined rule, then the procedure is going to get stuck. And then you have to make the worst case assumptions. On the other hand, if you leverage SMT solver, so it's very general in the sense it doesn't make any assumptions. And it's also going to be very precise in the sense that every time it gives you a counterexample, it's going to be definitely proved to be either safe or unsafe. But the problem is that it doesn't scale, right? In a sense that even with a tiny constraint system, if you throw to even off the shelf like a SMT solver with finite field theory, it's going to choke the solver. And so how are we going to do here? So our solution is actually like very intuitively. So what we do essentially, we build a domain-specific solver for ZK. So in this case, you can think of the idea is actually trying to mimic how human brain works in the sense that we know that as a human, we have left brain and right brain. So, and each of the different part like correspond to a different kind of reasoning. And then the final decision made by the human is essentially it's kind of interaction between your left brain and right brain. And it's the same intuition here. So in the sense that you can think of the domain-specific solver is going to incorporate those two components. In the sense that you get started with the original circuit, and then you try to perform some certain kind of rule-based reasoning as many as possible until you reach a fixed point, K prime, which is essentially the uniqueness signal that you can prove by far. Okay? And then if the output signal belongs to K prime, then you are done. Otherwise, you are going to pass this information to the SMT solver together with the original circuit. And then the SMT solver will further perform reasoning, which will give you an update version of K double prime. Okay? So in this case, you're going to check whether the output signal is going to be in the K double prime or not. If so, then you are done. Otherwise, you are going to update the original set with the K double prime, and then you provide this as a feedback, and then perform like a rule-based reasoning. And this iterative rule will keep going until you reach a fixed point, in the sense that you either prove the circuit is safe or unsafe with a counterexample, or you say that you don't know. Okay? And so there's a lot of more details about this work, but the high-level idea is essentially we combine the strengths of both rule-based reasoning and SMT. And so does it work? So we actually evaluate on two extensive data sets. The first data set is from Circon medians, what we call Circon median, which essentially contain 66 benchmark from Circon lib. And then the second is from Circon hard, which contain more benchmark with larger constraint, in the sense that constraint with tens of thousands of elements. And so, and for the baseline, we consider two variants on SMT. First, we use CVC5 with a finite field theory developed by Alex from Stanford. And we also use Z3 with the native non-linear arithmetic. And for the root, we directly use a root from Acne at 0xPath. So which means that every variance of the Turing is going to produce three possible outcomes, either safe, unsafe, or we don't know. Okay? And so far, the preliminary result is kind of promising in the sense that if you run a naive Z3 solver with non-integer linear arithmetic, it can only solve 22% of accuracy. Okay? So the y-axis corresponds to accuracy. Whereas if you try the rule base as well as the domain-specific, the SMT with the finite field solver, you solve certain amount of accuracy by around 70%. But when you combine them together, you can actually get around 90% of the accuracy. And so when we move the same evaluation to a more complex benchmark, as you can see, the SMT solver start to choke. Like for instance, on the original finite field solver built on top of CVC, so the accuracy dropped from 71 to 44. But the combinations of both rule-based as well as SMT still does better than the rest of the elements. So in addition to the benchmark, we also evaluate our current tooling on a set of real-world like a ZK circuits that have been working with, including circle pairing, semaphore protocol from Ethereum Foundation, etc. So the takeaway is essentially we propose PyCast, a fully automated tool for finding under-constraint bugs. And then, so the key insight is essentially we leverage expert rule as well as SMT reasoning in a synergistic way. And so you're welcome to try the tool. And then for more details, please follow us on Twitter. Thank you.
Yeah, very interesting. I had two questions. One of them is, I guess you set a timeout for how long the SMT solver is allowed to run?
Yeah, the timeout, very good question. The timeout, we have a total timeout, which is essentially 10 minutes. Mm-hmm. And we also set a timeout for each query. Mm-hmm. For each query, we set 2 minutes.
Okay. And then I guess the other question is, did you find any bugs? Like, did you find any, in the things that you tested, did you find any under-constrained circuits?
We do. Yeah,
oh, yeah?
Yeah, we do.
Okay.
Yeah, I can share the details.
So the 91% is like the rest of the 9% are unconstrained, or it's undecidable?
The rest of the 90% is essentially are the one that we don't know.
Okay.
Like the tool doesn't terminate.
Okay.
Because they are too difficult. Yeah, yeah. Thank you.
Great. Thanks for a great talk. Okay, so now we have the last invited talk for today, and after this we have another session on contributor talk. So for the last invited talk after today, last but not the least, it's our great honor and pleasure to have Shafi here as an invited speaker. And Shafi doesn't need an introduction, as everyone here knows. So Shafi is a Turing Award winner and also is a co-inventor of Zero Knowledge Proof, which is the theme of today's workshop. So Shafi today will talk about some really exciting topic at the intersection of zero knowledge and law. So with that, thanks, Shafi.
Okay, hi everyone. So I'm going to speak on zero knowledge and the law. And I guess it was about 5 years ago where I started talking to actually lawyers, friends who were professors in law school at least. And they were very, very worried because at that time everybody was talking about this idea that somehow court cases or at least bail would be decided by some automatic risk assessment system. So, for example, in California, there was this very progressive, in some sense, proposal, which was, or bill, which was that instead of having cash bail, where you have to pay money, depending on your abilities and your crime to get out of jail till a trial, there would be a bail, no bail replacement, where it would be decided whether you should be granted bail or not, partially by a risk assessment system, based on historical data. And then you would think that the bail bonds would be against it. In fact, they were, big time, but they were assisted by people from ACLU and people who are really civil rights advocates, saying that they believe that this is it's better maybe, or maybe it's no, the quotes are all over the place, but essentially they're saying is that they are against this because it's going to use a risk assessment system. And all the lawyers really that I talked to were also against it because some of they said, what do you mean? All of a sudden there'll be these programs, we don't understand them, what are you guys doing, and so forth. In short, the Californians have voted this down. I'm not, I'm new to California, only 5 years. I'm not exactly sure I'm understanding really the whole logic, but okay. In any case, it meant for me, though, it was very interesting because it was there's an interesting intersection here. In that time, there's all these proposals that we might be able to make law more efficient. At the same time, we are replacing something that's been truly studied. And more largely, what is this intersection between algorithms and law? I taught some classes about it. And what I want to talk about today is a little bit of an outcome of those investigations. But rather than actually trying to convince lawyers to use risk assessment systems, I think, and having them tell us that we don't know what we're doing, I would like to say to them that, in some sense, they don't no, I'm joking, but a little bit, they don't know what they're doing, because there are a lot of a lot of verification and trust problems in law which involve digital information, where there's essentially something that we call verification dilemmas. That is that on one hand, there's a legal entity. It might be a potential contracting partner that you want to sign a contract as a company. It might be in court, a litigation adversary. It might be a regulatory body or a government. And you have some sort of legal dispute with them or a legal arrangement with them, which requires disclosing a substantial amount of sensitive information, which creates risk. Disclosure creates risks that the information will be misused. And namely, it won't be used for the purpose that it was given, but for other purposes. And that's called a verification dilemma, when on one hand, there's benefit for the disclosure because you want to maybe sign a contract with someone or you want to defend yourself in court, but on the other hand, there's a risk of disclosure of sensitive information. And when the risk is bigger than the benefit, then possibly you shouldn't do it. So there are different legal doctrines. We have not discovered this. Obviously, this is something that's very studied in the law, and there are different legal doctrines to solve these dilemmas. But we found in this work with Ken Bamberger from the law school here, and Rebecca Wexler from the law school, and Ran Canetti from BU, and Evan Zimmerman at the time was a graduate student, that there's time and time again areas of law where this tension between risk and benefit and the legal remedies just don't work. Okay, so they don't solve what they are supposed to. And our proposal, obviously, given the title of my talk, is to maybe look at cryptography and specifically at zero-knowledge proofs as a way to replace existing procedures. So essentially, in the rest of the talk, it's not going to be a very technical talk or at all technical, but it's sort of pointing out to one avenue where zero-knowledge proofs will be or can be useful in the future. And since a lot of the zero-knowledge work that's described here was started 40 years ago on this campus, something like 1980, and it's taken a long time, obviously. It's 42 years for you to have this conference. Maybe in 42 years there will be actually implementation of these legal dilemmas, but given everything you've done, I believe it will be sooner. In any case, so I say that this is true across the legal landscape. And there's different legal doctrines that rule these different areas, like privacy law, deal making, trade secret litigation, administrative law. And in these 4 areas, then there's this additional area I won't talk about. Again and again, you have these issues where a lot gets disclosed, a lot more than what you need in order to settle what you are after. So I'm going to sort of do a little bit of a deep dive into the privacy law and the deal making, but just for the purpose of making sure that we retain from, this is what really should be retained from this talk. You know, when I say privacy law, I mean usually cases where you give a lot of personal identifying information because you want to get access to some resource. And instead of just proving that you deserve access, you actually reveal a lot of private identifying information. There's a lot of legal discourse about this, PII information, personal identifying information, and what to do with it. Then in deal making, that's when we don't have a single party, but we have 2 parties. So not a single party proving to a government or regulatory body, but 2 parties who are maybe in disagreement with each other, or maybe they want to make a deal. And they need to reveal things to each other, and they're afraid, of course, that maybe in the course of revealing, the deal won't be made, but somebody else will find out about their innovation, about their market strategy, about whatever. So there's a lot of information, and then there are NDAs. Then in trade secret litigation, maybe one company claims another company stole its software, stole its idea. You go to court. Again, you have to reveal a lot more than you like. So it's not clear that at the end, on balance, it was worth it. And obviously, accountability of governments. And I'll talk about all of this and about how can zero knowledge help. And in some cases, we've actually even done a proof of concept. So we have some system implemented to address some of these issues. All right. So so the point being is that each of these settings point to a potential use of zero knowledge proofs instead of what's done today. Okay? And before I dive into it, I want to say that this promises not only that law will be made more efficient, as was in the case in the bail not bail argument, that these risk assessment systems will make it easier to to make these decisions, but it offers sort of a very a new and a nimble legal trade-off between verification and exposure. So whereas before it's an all or nothing, we're saying once you use crypto, zero knowledge, you're going to be able to be more expressive and more precise, and that's something that obviously is going to mean that there will be more policy choices around this, and needs a lot of discussion. And these are not discussion that we are going to do. This is discussion that regulators, policymakers should do once they understand what is available and what then they can discuss what the trade-offs are. In terms of government, it does allow. I'm not used to not moving, but I cannot move here. So it does enable, if so desired, greater accountability of government adversaries who might not only be computationally adversarial, but they have also law enforcement power. So there's some things they can do we cannot do, and that should be included into the definition of their adversarial power, such as device search and seizure, types of surveillances, gag orders, and so forth, crypto backdoors. So if you possibly were implementing in this scenario some sort of zero knowledge proof, the government could retain its power and yet be accountable. Okay, so privacy law. Let's just talk about privacy law a little bit, deep dive into that, and deep dive into deal making, and then we'll zoom out. So in terms of privacy law, so currently, in order to verify eligibility to access digital systems, where all they need to really check is that you're old enough, that you have financial capacity, and so forth, you need to expose identifying information. And what happens about that is that basically somewhere a lot of data about you is aggregated. And that is really the big problem. There's huge databases of personal identifying information. These things, even with best intention, tend to be broken into, and that's a huge problem. So I guess this is some, number that I think I read 2 years ago. It's probably higher now, at least judging for myself, that there's 1 of 3 adults will experience identity theft, 1 in 5 companies have malicious data breaches, and so forth. And this is not getting less, it's getting more. Just judging by the fact, you are all protectors of information, but you have skills. And more people have skills to use it in various ways. And existing laws, as I said before, like PIIs, essentially, what do? After you reveal your information, they have all kinds of laws in place to make sure that your information should not be revealed by a third party to someone else. So it's not a before, it's an after. So essentially, they completely do not reflect the fact, the insight that if your personal data is never collected, it cannot be stolen. And that is sort of the magic of zero knowledge, right? If we can actually convince these authorities that we have financial capacity, that we are of age, that we do hold a passport, that we have been vaccinated without revealing information, then it won't be stolen because it's never been revealed. So here is kind of a perverse example even. Apparently in California, one of the laws requires businesses to provide each customer access to data kept about them. And that's a good thing, right? This is a provision. So I can tell what data is being held about me. That's a good thing for fostering individual control. But the law ensures that only verifiable consumers have access to these rights via requests, which means that the data and the requests are all linked to your legal identity. So even when you mean to do well, you actually do this by means that reveal even more about your requests, about your legal identity. Can you hear me? People seem like they're straining. Yeah? You can hear me. Okay, good. So let's imagine if we had zero knowledge instead. What would be the advantages? We do away with the databases of aggregated information and attributes, which reduces risk of exposure, and we alleviate this legal bind and need to identify customers in order to verify requests like they want to delete their data, and now you have to verify who they are. It's a bit problematic, It's sort of a... So more generally, it will be self-sovereign, selective disclosure of information. Of course, you need to implement this. But from what I've heard, you are doing it. So there's a lot of technical building blocks, even for statement of this sort, which would be efficient zero-knowledge protocols about quality and inequality of statements, numerics, conjunction of attributes, range, like if your data is in a particular range, are you a member of a list or not a member of a list, are you a member of a union of lists, intersection of lists, and so forth. So just to make sure that we're all on the same page, I think we are. This individual wants to prove at passport control that they are a citizen of an EU country, not which one, just that they have a EU passport. So that's a hierarchical maybe data where you just want to prove that you're somewhere in the hierarchy, and that more than 18 years old, I've been vaccinated, and I have money in my bank account. These are a conjunction of a whole bunch of statements that you can imagine how you yourself probably could go home and write down a program with digital signatures, verification, and so forth to do that. And then you just, prove it. Whether you do a snark or an interactive, I don't really care. That's already a question of I care, but that's not the topic of this talk. All right, so second one, deal making. So here we move from the having one entity proving to, let's say, government or regulatory form or a bank. There are two people, and they want to make a deal. Maybe they want to, but the deal is that the one company has to go outside of its boundary to make the deal with another company. What could be the deal? Maybe they want to merge, maybe they want to acquire each other, maybe they want to just explore what economic economic opportunities. Dan knows why I'm laughing. Okay, so what economic opportunities are there by dealing with this other company? So what do you have? You have two options. One is over-disclosure of information beyond your boundary, company boundary, and two is don't disclose. But then, what does it mean? You exclude individuals from participating in opportunities. You preclude firms from attracting capital, engaging in partnerships. Essentially, you also discourage oversight because some of these deals or negotiations enable you to have some oversight about companies. Once you don't do that, the oversight is gone. So the current mechanisms are NDAs. There's trade secret law. So trade secret law governs a lot of this type of negotiations. It puts a cap on how much you are allowed to disclose information that was revealed to you during some kind of a negotiation. However, these are all ex post. So if somebody doesn't do what they're supposed to, you can go to court. That is expensive. That takes time. Often it just won't be done. And second of all, it's insufficient because it's very hard to, write very precisely what it is that you're protecting under an NDA, and very hard to even put a price on how much you've lost afterwards when you go to a lawsuit. And all of this is not academic. For example, there is this famous case called the Target Smart case. I don't know how many people have heard about that. It's an ongoing legal battle where there's one company representing the Democratic Party sued a rival over alleged theft of trade secrets. So what happened here, this is this Target Smart company alleged that a rival company called Catalyst engaged a Boston-based company called Harbor Partners that specializes in corporate mergers to come out to them to talk about the fact that this company A says the company C told them the company B wants to merge with them, but in order to do that, they had to find out all kinds of information. And they learned trade secret, and then they shared it with the company that supposedly was not even present. So this is a case that's ongoing. And it makes it sort of worse than just two people are trying to make a deal. It's really using this as a fishing expedition in order to find out information in a very blunt and explicit way. In that case, it was to do with elections. In fact, in 1962, there's some famous body of work by Arrow from Princeton, economist, where he talks about economic welfare, allocation of resources for invention, and he explicitly names this problem. It's called the fundamental paradox of information disclosure, where there's sort of a little piece of text here from a paper, later intellectual property law and the boundary of the firm, that talks absent legal, that sort of summarizes what Arrow shows. And he says, absent legal protection, the information holder is in a bind. In order to sell the information, she must disclose it to the potential buyer, but once she does, she has nothing left to sell. So the paradox of disclosure, the fundamental paradox of information disclosure of Arrow essentially says there is no way you can disclose information without legal protection. But we already know that legal protection is not sufficient. And there's lots of economics papers written about this, about what is the boundary of the firm, how far can you go in terms of mergers, acquisitions, given this particular paradox. So we, again, propose to use zero knowledge to make a deal. And obviously here is, what is it that you're trying to hide? What is it you're trying to prove? That's the big question. But you could imagine that you could decide what it's okay for you to disclose, okay? And what prove the rest in zero knowledge. So some examples might be you want to talk about numbers of customers, like characteristics of customers or sales, attributes of company finances, profit margins, future commitments. Maybe you want to talk about your new product and you want to just partially reveal features and prove that maybe the full product exists without actually exposing it. So the hope is that this will minimize disclosure. It will enlarge the opportunity for startup financing opportunities, business opportunities, and it will lower the cost, essentially, of transactions between firms so that we could violate that equation that we had with the dilemma. So where the cost of transaction, whether it is cost to actually hire lawyers and have NDAs in place and so forth, or it's the cost of losing business because you've revealed, is lower than the benefit. And the dream is, of course, that there'll be successful development of meaningful applications for zero-knowledge proofs in this area. And I would go further and say that by talking to economists and lawyers, I could even imagine that this will have even a transformative effect on the market structure itself once they believe that you can go beyond the boundary of the firm. This is kind of daydreaming, but as we discussed, 40 years ago, was also a little bit of academic. Still, who knows? Things have changed. Technically, when you talk about things like deal making, which involves two parties rather than a single party, then you may require more cryptography than just zero-knowledge proofs. You may require multi-party computation, FHE. For example, in mergers and collaborations, you have to agree which partial information you should give each other. Maybe even agreeing which partial information depends on your secret information itself. So you could imagine a situation where there's a multi-party protocol that depends on what you have to decide on what you want to reveal. Then you could add zero knowledge on top of it to make sure that parties verify the information obtained in the MPC protocol and so forth. And in a trade secret where let's say two companies appear in front of a judge, it's very clear that you need some sort of multi-party protocol. Or rather, in this case, you have not a single prover. I think you've talked about this during the day today, but two provers or two companies, they each hold a part of the witness. Let's say two companies have software. One claims that the other one stole their software. It's very close to their software, but they don't want to reveal to each other the software. And then there's an arbitrator who's the judge. And all of this can be publicly verifiable, secretly verifiable, efficient, not efficient, and so forth. Okay, so obviously everybody here who is sort of practically minded says, wait a second, that's very nice, but there's lots and lots of challenges here. First big challenge is how do you link the proof to the ground truth? There's something that's really true about the company, how much money they have, how many employees they have, what are their patents is easier, but how do you link it to ground truth? So that's a big question. But I can imagine offhand a few ways to go about this, to have corroborating information and check it against it. So I think, for example, in Boston, they had this project about average salaries of women versus men in companies, and people were just reporting what the salaries were. But you could actually have a database where employees are reporting their salaries and check against it. And that would be just one example. And then you need things like digital signatures signed by maybe trusted third parties, devise a separate maybe verification auditing process with higher stakes, so maybe there's a penalty down the line if you don't do what you're supposed to every once in a while. Then there's a lot of details. They're not details. They're very important. But let's call them details for this slide. And that is, what commitment do you use? What's zero-knowledge flavor? Public verifiability, transferable, auditable, single prover, many provers, and who the stakeholders are. Who are they? Who are these alleged provers and verifiers? In the business engagement, in a trial, in interaction between the government and an individual. So what are their legal powers specifically? We like in the math world to say they are someone who has a computer, they know algorithms, and that's it. They're computationally bounded, but they have actually legal authority, legal powers. That has to be specified in a case like this as well. So these are really the least of our problems in some sense. These, 1 minute, okay, I am almost done. These are the least of our problems because there is really a question of, we can come up with lots of ideas, beautiful ideas, but in a legal setting, you have to ensure that the entities really believe in statistics and probabilities. Because of all of the things we talk about, there is a probability that we are proving a fact which is false, right? There's soundness error, and there is zero knowledge security breach error. And in courts, if you look sort of historically at court cases, there's a really not a very good understanding of numbers and statistics, and obviously that has to change. Another thing is, more fundamentally, how would legal scholars actually fundamentally view this idea that you decouple the verifying a claim from knowledge of the facts? I mean, there's a whole body of law and evidence, you know. How is this evidence? How does this really, how do you view this? I think this is actually fascinating, whether this would be acceptable or not, you know. As a mathematician, you think, what's the difference? Well, I don't think that that's a sentiment shared by everyone. Now, in terms of this is actually not a pie in the sky so much. So there's a paper on Usenex 2017 with Jonathan Frankel, who's now, I guess, faculty at Harvard, Sanu Park, and Daniel Schall, and Daniel Weitzner, who's also faculty at MIT, was about how do we build a system that checks and balances surveillances, that surveillance orders are eventually, the gag orders are lifted, and you're able to check that, in fact, how many surveillance orders were given out, for what reasons. These days, there are company reports, Facebook and so forth. They say we've been requested surveillance X number of times but how do you check that? How do you verify these claims against, let's say, other information coming from the court? And lastly, there's a paper that Dor Bitan, here as a postdoc here now at Berkeley, is going to talk about on Tuesday in front of a legal conference, more CSN law. And I know I'm maybe above a minute, but I still want to say it. And that is a specific problem, and he's built a system for it. And that is, suppose, and this is something that's, again, has come up in courts, there is someone who's engaging in illegal activity. Let's say there's a suspicious pornographic activity, and the FBI has planted some software on the computer of this alleged pornographer, and now they have evidence, and they get to court. So one of the things that a defense lawyer may say, and has said, is I demand to check the software. And I'm allowed because to determine the lawfulness, constitutionality, and accuracy of the investigative tools used. Now these guys, the FBI, obviously will say, I can't. You know, this is my trade, this is my tool. I need to use this again. And there's even legal body that says the disclosure of investigative tools might enable future criminals to evade detection, therefore they shouldn't. So what should be done? It's very unclear, right? You know, on one hand, you've got the law, on the other hand, you've got the defense lawyer, and what should be done? So there's sort of three choices. You know, order disclosure of the software. What has happened in several cases is that the FBI says, okay, forget it, then we don't continue with the trial. You could proceed based on the officer's affidavit. That's not desirable either. You could get an independent expert. I think that also leaves things to be desired, because it's not clear the expert is going to be agreeable for both sides, yes or no. So what about zero knowledge? It's kind of an obvious question, but it's not so obvious because there are lots of questions of what the defense wants to check about the software. What do they want to check? Is it that it's buggy, that it's changed the PC setting of the defendant, that it planted a virus? Maybe they even didn't use this program they claim they used. Notice that some of these issues come up even without today, when you hand to the defense your software. And what we do in this work that I'm not going to present, obviously, is that we focus on one manageable instance of this, you know, sort of one of these things, and sort of propose a design of what an investigative tool should look like so that it can be easily you can prove things about it in zero knowledge. So part of that is also saying, okay, you know, there should be a format to this. It's not the Wild West, and if there is a format, then we can actually check certain things. So I know it's the end, but this is really comic relief, and I think you need it at the end of the day. So the son of Omer Reingold, can you have voice here? Not comic relief. It's actually interesting that this is made it popular culture. Yeah? Is there a way to do that?
Where the SEC is asking to get access to the company's trading company. Your Honor, I'm simply requesting Mr. Sutton hand over something he has no right to. I have every right to make sure that your client is operating within the law. And what exactly is your basis to say you need? Your Honor, when you break the home run record and someone says your bat is corked, you turn it over to show it's not. Except when that bat is the reason you hit all those homers. Because the second he gets it, everyone in the world's going to know what's in it. And my client
So you get the point. There is actually an interesting, even though it's a TV show and so forth, there's an interesting case here where they're saying I'm saying there's an interesting case here besides the fact that it's popular culture, TV and so forth, which makes it accessible actually. But there's an interesting case here where software might have been just way too successful, it seems. And what the one lawyer is saying to the other, I don't believe it. I think you have violated some basic rules. And hand me the software. Obviously, you don't want to hand the software. But possibly you could prove that your software has certain qualities without handing it over. Thank you.
Thanks a lot, Shafi, for this amazing talk. Shafi started ZK Zero Knowledge Proof, and it's great that Shafi is bringing this to the broader domains, including law. Thank you. Any questions while we set up for the contributor talks? Do we have any one last question?
I actually would like to know, like, who do you? I've been talking to a couple people in Italy, and maybe Italy is not like the place where it's literally projecting onto the future in this field. But who do you get to talk to? Do you go to like a conference of lawyers? Do you publish their papers? Do you try to explain to them the knowledge proofs? What kind of approach have you been taking?
So actually, the three papers that I mentioned, they all are in conjunction with lawyers. So like Rebecca, her law expertise is evidentiary law. And so that's one thing. But there are conferences now. So there is going to be a conference in DC starting Tuesday, Wednesday, which is CSN law. There is, it's not the first one, I think it's the third one of that type, where computer scientists and lawyers meet to discuss these issues. Now, the next stage, of course, is having it in some sort of formal judiciary body, but it's not there yet. But also, actually, the surveillance aggregation one was motivated by a bunch of papers by a judge who claimed that a lot of surveillance orders essentially are never the gag order is never lifted. So, and he was saying this is not appropriate, that's not right. There's no way that we can check whether surveillance was done properly or not if we never have a chance to even find out that it existed. So there are people within law who also realized that they could get better. And he was actually excited about it, but that doesn't mean that then he brought it to a committee of judges, asking them what do they think about it, and they say, forget it, what ain't broken we're not doing. That's a question of judgment if it's broken or not, right? Yeah.
So one of the problems that people working in AI and law have known about since the 1970s really is that a lot of the concepts in law are what it's called open textured, just too fuzzy. They don't have if and only if definitions. Right. So maybe a lot of the things that you want to check on the information that is not being revealed is just too soft and to encode into a program. So have you thought about that?
I completely agree with you. That's why the cases that I kind of pointed out are not like that. So for example, that ID, what my age is and my financial capacity and whether I'm vaccinated and whether I have a passport, these are things that we can do, right, formally. Or in the case of maybe if there are two pieces of software that are competing, that's a very interesting question. Are they modifications of each other or not? Maybe there's a technical definition to what is the threshold of that after which you should reveal, the software. And but absolutely agree with you that this would be well suited for areas where what you are trying to reveal or trying not to reveal is very explicit and it's only part of the case and not the whole thing.
So during the last about an hour, so we'll have contributor talks. So given the time, so we're just going to keep 5 minutes for each talk and let the speakers come on the stage one by one. Thank you.
Hello, everyone. I'm Bobin from Polygon Hermes, and today I'm going to go and give a very quick talk about ZK virtual machines and some design considerations that go into them. Let me see. So the first thing is like, what are ZK virtual machines, and how are they different from other things that we can do in the ZK context? So I think to set the context overall is that there are many ways to think about the programs, but there are two specific ways. We can think about the program as a circuit, and then as a circuit computation, and then the program itself is basically becomes a circuit. You have some inputs, they flow through the gates, and you get an output, and that's your program. The other approach is to think about programs as executed on a virtual machine, in which case there is a circuit that defines the virtual machine, but the program itself is an input into this circuit. So there are two fundamentally very different models to think about how you can run computations. And we're going to obviously focus on the virtual machine one, because this is what the talk is about. So what is a ZK virtual machine? And let's start with just a basic virtual machine where you have some initial state, you have a program that is an input into the virtual machine together with initial state, and you get some final state at the end. In a ZK context, we get something else. We get a proof at the end. So this proof attests to the correct execution of the virtual machine, or of a program on this virtual machine. And then we also get this witness. A witness is something that can be a private input, but we can use it for other things as well. Like, for example, instead of providing a program as a full public input, you can provide hash of the program and then provide the actual program as a witness into the virtual machine. Now, what are the advantages of using virtual machines over some, let's say, circuit-based computations? And there are a few. So potentially, one of them is like ease of use. Once, a virtual machine can have like an instruction set that is very standard, like we understand how to write software and compile them to instructions. So, you don't need to learn anything about ZK or cryptography or anything of that to use a virtual machine. There is a universality to it where, if you have a Turing-complete virtual machine, that's all you need to be able to generate proofs for any computations out there. You don't need to design anything else. And that kind of leads to this, relative simplicity in a way that once you have your circuit defined, you don't need to do anything else. Like, you verify the circuit and you don't need to build another circuit. Everything else is just a program that gets executed by this program. And then once you have this Turing-complete virtual machine, you also get recursion almost for free because, if a instruction set of the VM is powerful enough to verify a proof of its own execution, that's infinite recursion right there. You don't need to do anything else. There are some drawbacks to using virtual machines, and the first one is that you need special, like for it to be efficient, you need some special structure to the computation. It's a very regular computation. You ideally want to have a proving system that is tailored to that. One of the proving systems that works very well for this is Stark's, where it assumes a regular structure of the computation. The other thing is performance. Because you need to do some extra stuff within a virtual machine, you might lose out on performance because you need to decode the program, for example. You need to perform other things like memory access, which not all computations may need that. But we can actually alleviate this somewhat by building specialized circuits. I think Jeremy from RISC-0 was talking about accelerators. So we can, for example, have special circuits that are very efficient in doing specific things and optimize them on the VM. Now, to go through some design considerations of like what we want to think about when we build a virtual machine, I think the first design consideration is which instruction set you want to use. So if you go with something already well-defined, like EVM instruction set or RISC-V instruction set, that the questions are kind of like very straightforward to answer because you already know what you're building. But if you're building something new, which is, frequently makes sense because you're building something for blockchains, for example, or in a specific context, there are other considerations. And for example, which machine type you want to have. Like, there are stack machines, there are register machines. And in a ZK context, for example, memory access is really cheap. So you can actually do a memory machine where there is no stack, there are no registers, it just goes directly to memory. And this is very different from like a traditional hardware design. You want to figure out what control flow, methodology you pick. You can have Harvard architecture, you can have von Neumann architecture, but you can do something else. Like in Maiden VM, we use this Merkleized abstract syntax tree, which is a very different way to represent the control flow of a program. I mentioned this in the beginning, like you can initialize programs in different ways. Do you provide a program as a public input, and there are pros and cons with it? Do you provide just a hash of the program and then kind of like invert the hash inside the VM via non-deterministic inputs, or do you do something else? So that's another design question. How do you handle function calls? What is your memory model? So for example, you can have a write once memory, which is super efficient from a cryptographic or constrained description standpoint. And this is like some virtual machines like Cairo, for example, do that. Or you could have read-write memory. It's a bit more complex, but it gives a kind of more familiar environment for compilers to compile into and things like that. And then there are a bunch of other things like, what native data types do you support? Like we'll work in finite fields, so you have field elements as almost always available in the VM. But also, do you want to support regular integers? Do you support like structs, arrays, and how do they work within the VM? I think those are like some important choices. And then, what is the field choice? And then the last thing that I want to say, like, what did we choose for Maiden virtual machine? And specifically, the ZKP proving systems, we use Starks, which are very efficient because, as I mentioned, virtual machine has a regular structure, and Starks are very well positioned for that. But we also use this multi-set checks. It's an additional kind of, addition to the Stark protocol, which allows us to tie different parts of the VM together in a very efficient way. Without the multi-set checks, it would have been very, very difficult to build an efficient virtual machine. As a prover, we use this Winterfell prover, which is a general-purpose prover written in Rust. It's very efficient, and it's kind of very easy to use. For the field, we've chosen Goldilocks field, which is a very efficient 64-bit field. Daniel earlier today was mentioning how it's well-suited. You can do most reductions in just 2 CPU cycles for multiplications and things like that. So it also is a very nice field because, like, if you multiply 2 32-bit integers, it doesn't overflow field modulus, so you can handle 32-bit arithmetic very easily. And then lastly, as I mentioned for Maiden, we decided to go with our custom instruction set, which is a bit more ZK optimized and specifically tailored to some blockchain applications. So we didn't go with one of the kind of already established instruction sets. And we used this mask-based program, which allows us kind of to mix, like you can, one of the advantages is that you can hide parts of the programs very easily where, first part of the program is known and the last part of the program, for example, is known, but the middle is completely hidden from the verifier, and you can still verify the execution of that program. So I think I went a little bit over 5 minutes, but yeah. If there are any questions, I'm around here.
Time then we'll take questions offline. Thank you. Yeah. Next will be Shumo.
Hello. Good afternoon, everyone. Very honored to be invited here to give a talk on the Polygon VM. And let's get started. Right, first, a little bit about Polygon Labs. Our mission is to bring privacy to every Web3 project. And we deploy a Manta network and a Calamar network at Kusama and Polkadot ecosystem. And today I'm going to talk about Polygon VM, which is our research project. I'm the co-founder of the project. Okay, so why I'm here, right? I think the mission here is to bring the next 70,000 ZK apps to Ethereum. So if you look at the ZK application landscape, right, I can briefly categorize into kind of 3 categories. One is for privacy. And of course, there is a OG privacy coin Zcash, bring the concept of the shielded pool. And also there's Manta, Alio, and ZK Opera from Ethereum Foundation, Aztec, Espresso Systems. And also we're using the sort of a compressing mechanisms of zero-knowledge proof to do scaling, for example, ZK Sync, Scoretex, and Polygon Hermes. And also there's, we can see increasing numbers of people doing attestation, including like Anonymous Social, for example, Sysmo, Axiom, and HyperOracle, right? So I guess my question here is that I think we need a further democratization of ZK app development. Right. I think we see a huge problems in the space right now. So for example, more specifically, these 3 problems we're trying to address right now. First is a higher barrier to entry for ZK development. And second is high gas fees, even L2s, right? If you talk to all these zKEVM teams, right, so most of them haven't implemented a BM precompile, which is pairing for ZKP verification on L2, right? So even in the existing L2s like Optimum and Arbitrum, there is a huge ZK verification cost incurs. And third is lack of toolchain support here, right? So here, allow me to do a brief survey, right? How many of you have written a Solidity contract, right, including any toy program? Okay. And how many of you have written ZK circuit? Right, so you see the disparity here, right? I think the fundamental reason is not we're lacking DSL, we have like NOR, we have CIRCOM. I think the fundamental reason here is that if you're writing a ZK circuit, essentially you are developing cryptographic protocols, right? You need to understand the security considerations. You need to understand security parameters, right? Of course, everyone should watch like Dan's Intro to Cryptographic MOOC in the Coursera to get an understanding. But still, right? We don't think every application developer should write the ZK circuit, right? So what's our solution here, right? So this is Polygon VM design goals, right? To kind of fight the high barrier to entry for ZK development, we want to provide layered programming abstractions, right? So we think there need to be many layers of programming abstractions for the ZK application developers. So I think briefly there are 3 layers. For time's sake, I will probably just have time to go through a circuit layer, But in general, there should be a storage layer who have efficient storage access for a ZK-friendly storage. And there's a circuit layer is kind of like a, for lack of a analogy, a library for people to use. And then there's the app layer. I'll get into more details. And secondly, for high gas fees, or even L2s for high prover costs, we need dirt cheap ZKP transactions. And third, for lack of toolchain support, and we want to support kind of like a maximum EVM compatibility to leverage the existing Ethereum toolchains, for example, MetaMask, Hardhat, EastFold, you name it, right? So, okay, let's actually get into the Polygon VM architecture, right? Basically, I'm a computer science nerd. One of the computer science projects in the history kind of inspired me, the Unix operating system, right? Basically, here I propose a VM architecture kind of mimics the Unix operating system, right? In the base layer, you have the file system layer, and in terms of ZK app for a ZK app developer, we want to have ZK-friendly storage. More specifically, like for example, like Merkle trees using Poseidon hashes. And in the middle layer, it's kind of like a C layer, right? That's a missing library layer. So we want to deploy circuit, and we want to deploy circuit that can be composed freely from the application developer point of view, right? Using the Unix analogy, you kind of see, right? In the Unix, you have bash, you have cat, and also in the app layer is Solidity, right? So I have 1 minute left, so I will be roughly quick. I think the solution here, how do you solve the library layer here? The problem here is that how can you compose ZK circuit together, right? Naively, you can just smooshy the code together, and they share the public input and private input. And here, we're actually proposing using a technical CP snark. This is actually from the 2019 LEGO snark paper. So the brief idea here is that, let's say you have a 2 ZK circuit. Instead of the kind of becoming isolated island can only be application specific. So they actually can share a re-randomized commitment. Basically, the same is 2 circuit kind of opening the same re-randomized commitment inside of circuit, kind of like this re-randomized commitment as a kind of like a pipe, so that these 2 ZK circuits can talk to each other, right? So without loss of generality, let me actually show you an example, right? So this example is for ApeFest 2023 location vote, right? So suppose all the ape holders want to vote anonymously, right? Here, we can compose 3 circuits together. So the first circuit, basically, ZSP is short for ZK Ether shielded pool. Basically, you first prove that you own this piece of UTXO in the shielded pool, right? And also using the re-randomized commitment. And second, called CAD. CAD is short for configurable asset disclosure, in the sense that you prove you own this piece of NFT, and this piece of NFT is ape, right? But you don't disclose which specific ape you own. The next is kind of like an external nullifier circuit. You basically prove, hey, I didn't double vote in this specific event, right? You can see in these 3 lines of code, from the Solidity developer point of view, the Solidity developer doesn't need to even to write a ZK circuit. They just need to understand the semantic of the API, and then just write a vote, right? So, so for time's sake, I think this is one thing I want to show you. Basically, we want to have a missing ZKP library layer for the Ethereum, so that people can, the high-level programmers, application developers, like Solidity developers, can just write Solidity and building ZKP-based applications. And yeah, so to conclude the talk, I present Poseidon VM, the VM to bring in like 70,000 ZK applications. Want to show you we should do layered programming abstractions for ZK app development. Want to have dirt cheap ZKP applications, and also we want to have a maximum EVM compatibility. Right. Thanks.
Next one will be. Oh yeah. Next one will be from Polygon.
Okay, hi everyone. This is Boyan from Poseidon Lab, aka Manta Lab. So today I'm going to talk about accelerating MSM operations on the WebAssembly. So the first question is, why WASM? So basically nowadays we see many ZKP dApps. For example, the private payment, the anonymous voting, anonymous social, all this stuff. So basically, if we want to protect privacy, we need the user-side ZKP proof generation. I mean, different from like the many scaling solutions, this solution can send the user data to some server and use this very high-powered server to generate the proof, right? But if we want to keep privacy, we want to make sure that the user data never leaves the user machine, right? So the user need to generate the proof on the user side. Usually not so good. There's no GPU, no FPGA, no ASIC. In addition to that, users also want browser execution. People usually don't want to download some binary for only generating the ZKP, right? Also, people usually want the MetaMask integration since they are already familiar with this, this interface. So we need Wasm for the ZKP deployment. So what is Wasm? Wasm is a virtual machine for the deployment on the web. It is also a portable compilation target for programming languages. And we can have ZKP with Wasm. So basically, it brings very low user friction. We can generate a portable binary file runs in the browser, for example, with JavaScript. It can also be integrated into MetaMask with MetaMask Snap. The user flow would be very similar to all the dApps nowadays. But the problem is the performance concern. So one way is to use a Webpack. We can use Webpack to compile the Rust code to Wasm, right? But there would be some slowdown. For example, let's say, for example, the ZKP private payment from Manta. If we run it in the x86, it only takes 2 seconds. But if we compile it to the Wasm, it would take 20 seconds, right? There is a 10 times slowdown. Users usually don't want to wait 20 seconds to generate ZKP for every transaction. So we need faster ZKP in Wasm. And if we think about the computation in ZKP, actually there are two important operators. One is FFT, one is MSM. And usually, MSM is much slower than FFT on the same input length. For example, if we think about 2 to 14 inputs on the Wasm, FFT takes around only 100 milliseconds, but the MSM takes 3,000 milliseconds, right? So we want to make MSM faster first. So we hold a zPrice Wasm computation. We serve Manta serve as architects, along with Polkadot as sponsor and several other startups. We want to raise attention and find a solution for this ZKP performance on the Wasm. Now I will talk about Manta's optimization for this performance issue. We handwritten the Wasm for MSM. Basically, we handwritten the assembly code to try to improve the performance. Actually, we start from the MSM in the Wasm curves. This is developed by the Wasm curves is developed by the IDEN3. It provides a toolchain for handwritten Wasm. Basically, it can map each line of the code to some bytecode. Also, it provides the MSM with Pipinjer. After that, we add many algorithm optimizations writing in the assembly code. The first thing is batch affine. Basically, we can batch many affine point additions to amortize the cost of inversion, so it's faster. Also, we have we add the efficient isomorphism. We can split, basically, for example, we can split one 256-bit finite field elements into two 128-bit field elements. In this way, we can reduce some computation. Also, we can make batch affine faster. Make batch affine easier to use. Another thing is fast CIOS. Thanks to Rahul from Jump Crypto, we can reduce the number of operations for the finite field multiplication. We also tune the bucket size in Pipinjer. Basically, we can balance the number of windows and number of buckets, make it faster. Actually, there are more optimizations we can apply. That's all the optimization we have now. It already gives some good performance improvement. Okay, now let's talk about the evaluation. The unit is millisecond. We measured on this CPU. Okay, this is the result. Of ArcWorks on the x86. It's kind of okay. But if we compare with Webpack to the Wasm, we see a 10 times slowdown. And if we use, let's say, the WebAssembly from the Wasserman curves, it's faster, much faster than Webpack, but it's still slower than the ArcWorks. And then we can add ByteCharFun, we can add GLV, also the FastCI OS and bucket size. And overall, we can achieve 5 times to 7 times faster compared with Webpack. This is kind of similar to the ArcWorks performance on the x86. It's only 1.5 times slowdown instead of the 10 times slowdown, right? So this improves the performance a lot. So basically, we believe that hopefully this work can make ZKP generation easier on the user machine. Yeah.
Hi, everybody. I'm going to talk about a architecture that we developed called Cyclone MSM for accelerating MSM operations on FPGA. This is work by a bunch of folks at Jump Crypto, Kaveh Asserai, Emanuele Cesena, and Nicholas Stalder. Also mentioned briefly that the optimization for CIOS was done by a bunch of other folks at Jump as well, so especially John Lin, who actually implemented some of this code. So why are we doing this in the first place? We're all in on scaling ZK. We really want to work with like real applications, real large circuits, and eventually develop something that's kind of close to something related like proofs as a service or proof of marketplaces that can enable other infrastructure to really grow and scale. And we think some of these applications are going to be related to fast chains, privacy-friendly chains, and also cross-chain bridges based on ZK technology, and data oracles as well that are based on ZK technology. And we're here to support that infrastructure. So what are the results? We got, for 2 to the 22 size MSMs, we got sub-second proof generation, essentially. So computing 2 to the 22 size MSM was done in less than a second. For 2 to the 26 MSM, that was done in 5.66 seconds. And so this was built on top of ArcWorks for BLS12377. And we actually ran this on an AWS F1 instance. And this was an FPGA that's quite old and doesn't really have good PCI bandwidth. So we were targeting the Z-Prize. So we think like with modern hardware, this could be actually accelerated quite a bit further. You can check out the ePrint as well, and for the link here. So how do we actually do this? So we implemented a fully pipelined EC adder at 250 megahertz. So this means you can initiate a new operation every 4 nanoseconds. So what was the architecture of this? So there were kind of 3 levels of optimizations. One was at the algorithmic level, and then kind of the next layer below that is at the elliptic curve level, and below that is at the field level. So we essentially converted all the points to Twistor-Edwards coordinates for BLS12377. And then we used Pippinger's method or the bucket method at the algorithmic level. We used, for the field arithmetic, we used like Montgomery multiplication. And so like this is a particular architecture that we used that was kind of well suited for the Z-Prize. But this is also a flexible architecture. It can be used for other systems as well. We actually implemented it and provided some context for it in the paper as well. We used batch affine, and that yielded a 10 to 20% improvement over the NARC crypto library. So yeah, thank you. Please reach out if you want to talk more.
Hi, hello everyone. My name is Jiahen Zhang. I'm a PhD student at Berkeley, working with Dong. Today I will talk about our recent work on scalable ZK ROPs via fully distributed ZKP. So first of all, let's talk about the ZK ROPs. As we all know here, ZK ROP is a very popular topic, especially in the industry. And there are several companies they are developing their ZK ROP solutions, and also some companies are developing the ZK ROP ecosystem to support ZK ROPs. However, we need the ZK ROPs need complicated statements and strictly large-scale circuits to support the variance operations in ZK ROPs. And the bottleneck of ROP is proof generation, because the proof time in the zero-knowledge proof protocols is still slow for the large-scale statement. And when natural directions to solve this problem is to use the distributed computing. As you can see here in this setting, we have multiple machines, and they will work together to generate the final proof. And each machine just runs a small piece of the proof, and it is much faster than the single machine generating the whole proof. And and there is a previous work of the distributed zero-knowledge proof protocol called DIZK by Howard and other researchers in 2018. And in their scheme, they designed distributed algorithm for zk-SNARK, and their scheme could scale zk-SNARK to over 100 bigger circuits, which is pretty good. However, it still has some limitations. Firstly, the overhead on the prover time is still prohibitive for large-scale circuits. And also, the communication among different machines is also high. To address these problems in DIZK, we designed, our work is focused on designing distributed algorithm for Planck, while Planck is one of the most widely used ZKP protocols in the industry. And in particularly, we designed a new version of Planck with multivariant polynomial encoding instead of the univariant polynomial encoding. And then with this this approach, we can remove the FFT operation in the original Planck by multivariant sum check. And then we replace the univariant polynomial commitment by the multivariant version. And underlying this protocol, we also have a new permutation protocol with linear prover computation, which may be of independent interest. With this scheme, we have some good news for the multivariant Planck. The first one is we have the linear prover computation in our scheme because we use the multivariant sum check instead of the FFT. That beats the original prover, quasi-linear prover time in Planck. And it is also fully parallel because the schemes used in this protocol are friendly to distributed algorithms. And I'd mention here, there is a concurrent work of HyperPlanck. I think Dan also mentioned this work in his talk this morning. And we obtained the similar results from different perspectives. And also, we have a new result on fully distributed Planck without modification on the univariant polynomial encoding in Planck. But I don't have time to dive into details in this talk. To summarize, we designed the fully distributed ZKP protocols for Planck and multivariant Planck, and our protocol achieve optimal linear scalability as well as minimal communication. And our solutions can be used in the zk-ROPS mining. And that's all. Thank you.
Is this my button? Does this go forward? Does this go back? Cool. Thanks. Hi, I'm Sam Dittmer. This is joint work with Yavali Shai, Steve Liu, and Rafi Ostrovsky on line point zero knowledge. I did my graduate work in math, not in computer science, so that's my background. In math, I was taught that you should keep the first 15 minutes of your talk accessible to everyone. The next 15 minutes should only be accessible to graduate students. After that, the next 15 minutes should be accessible to experts in the field, and the last 15 minutes, nobody should understand, not even you. Fortunately, I don't have a full hour, so we're gonna keep things general, and in that spirit, we're going to begin with a simple statement. The universe is very big. Of course, we mean the universe of zero knowledge. To this, we can talk about Yupeng's earlier comments. We have a whole bunch of things. Garbled circuits, MPC in the head, zk-SNARKs, the big rollout there. And where in this does line point zero knowledge fit? Answer, it's in this galaxy of vol-based designated verifier NIZKs. Where is LPZK in this picture? Answer, it's there. Okay, so what do we mean about this galaxy? What do we care about? Okay, so what is vol-based designated verifier NIZK? It's non-interactive. It has a pre-processing-based correlated randomness called vector oblivious linear evaluation, or VOL. And It takes linear communication, and you do that in exchange for a really efficient prover, and you need a designated verifier. Why would you care about any of this? Well, the big reason we do this is we want concrete efficiency. We get a really fast prover. It's small memory, meaning that if you have a circuit, you basically pay the same price in space that you need for the actual circuit evaluation. You don't have to store the whole gates in memory all at once. So it's compatible with streaming operations. So if you're on a really fast network, then maybe computation is actually the bottleneck and not communication, so that's why you would care. The efficient vol-based preprocessing works well in the online-offline setting. And finally, we will say that it's a quantum secure candidate, because that's something we care about. Another way of explaining what line point zero knowledge is the following picture. It's a line with a point on it. The prover builds a line. The verifier queries a single point on the line and can determine whether to accept or reject. The catch here is that the line is in a very high dimensional space. That's where the big computational cost is setting this up. Now, if you remember from Dan Bonnet's talk about interactive oracle proofs, where you have the interactive oracle proof versus the cryptographic machinery, using the metaphor, this is the IOP, and the machinery is a vol. There's the picture of a vol. And it's a functionality where you input two vectors, and the receiver inputs a field element, and you get this expression A alpha plus B, which should look familiar from the previous slide. That's, again, a line. And the reason we care about this is that this can be generated efficiently using this lightweight sublinear communication protocol from BCGI 18, and there have been a bunch of improvements in vol generation, Silver, and other work in the last few years. I'm going to give a very quick overview of the actual construction. Here's a picture of a circuit, and you encode each entry of each wire of the circuit as an entry of the vol. So you have two vectors. One vector is random. One vector is your circuit wires. And so there you have your A and your B. And so if you remember, it's A times alpha plus B equals V. So then you do some math, which we will not look at too closely. But the verifier can compute these expressions, A alpha plus B times A j alpha plus B. The prover can compute the same expressions over a formal variables. And then you know that they will have the same zero coefficients if and only if the prover is honest. And so you just have to check that these things have the right degree or have zero constant coefficient. Finally, we will discuss very briefly our results. I'm going to skip this slide because this slide carries almost the same information. We don't have a lot of time. So these are a family of vol-based zero-knowledge protocols over the Mersenne prime, 2 to the 61 minus 1, which we choose because you can do a whole bunch of cool hacks where you get mod reductions really fast. And we draw attention to the information theoretic version of LPZK. We get to around 20 million gates per second, which is like 50 nanoseconds per gate, which is very fast. This is just for generating the proof. It doesn't count the communication time. But we have one more chart. And I like this chart. I guess I made it, so I should like it. But this is for 1 million gates, the communication, the prover time, the verifier time. And the last column means how fast does your network have to be before you care more about optimizing for computation rather than communication. So if you have like a gigabit of speed, then at that point, communication is no longer the bottleneck, it's computation. And so if you're in that setting and you're willing to tolerate large proofs and you have a designated verifier, at that point you should be interested in something like LPZK. Thank you for your attention.
Thank you. So next we have Vinny to talk about hyperplot.
Okay, so hi everyone. I'm Bing Chen from Espresso System. Today I'm presenting Hyperplonk, which is a variant of Plonk proof system that with some very nice features. This is joint work with Ben Capons and Dan Bonnet and Chen Feijian. So essentially, we built a new type of IOP protocols that adapts Plonk onto the Boolean hypercube, or more precisely, to the multivariate setting. This enables us to get a very fast time prover that has linear time, and the scheme is also very highly parallelizable and hardware friendly because we fully remove the use of FFTs, which has caused linear time complexity and can be less parallelizable when the instance size is large. So this makes it very favorable for applications like zk-ROP, zK-EVM that has a gigantic circuit size. So second, we also provide much better support for high-degree custom gate. As mentioned by Dan in the morning, that like for now we can model much more complex computation into a smaller number of gates and without sacrificing the proving speed per gates. Okay, so and also the resulting snark has very good concrete proof size compared to most of the multilinear-based snarks. It's only like 6 to 7 kilobytes for all types of like applications. Okay, so second, we also extend Hyperplonk to also support another types of custom gates called lookup gates, and obtain the first linear time protocol for lookup relations. It's useful for like a lot of other applications like rank checks and standard, like proving correctness, standard hash functions, so on and so forth. Finally, we also build some new multilinear commitment schemes that can all be plugged into these Hyperplonk IOP protocols, then obtain different kinds of snarks with different kinds of features. One highlight is that we improved the recent Orion-based polynomial commitments from the linear critical code, which has a really fast linear time prover. And our improvements that we've preserved the linear time prover, but we improved the proof size from like several megabytes to several kilobytes, which is almost like a 1,000 factor improvement. Okay, so for time reason, I'll focus on one cool feature that we achieved, which is the lookup gates. So given two vectors, f and t, how do we like efficiently prove that every element in the F is inside the table T? So PoolLookup is a really elegant paper that solves this problem by interpolating these vectors onto a polynomial on a set H, which is a multiplicative group generated by a root of infinity, and transform this lookup relation into another type of relation called multiset ecology check, which basically is saying that we want to show that two multisets are equal. So I skipped the exact transformation from lookup to multiset ecology check. But the key message here that I want to highlight is that this resulting protocol essentially makes use of the fact that we can efficiently rotate the valuation on a set, on this set H. So from FH, we can rotate it to F omega H so that every position is shifted by 1. And it's very easy and simple to do this. You just multiply the set by a root of unity. However, in our setting, the interpolated set becomes the Boolean hypercube, and the univariate polynomial becomes multivariate polynomials, or more precisely, multilinear polynomials. So the existence of such a simple linear generator function is no longer trivial. So our first step is to view this Boolean hypercube as a field, more precisely the field of binary extension field, which is f2 to the mu, and build a generator function on top of this. So we note that recently that like there's some like similar tricks has been used in other papers, but for other purposes. So let's see how it works. So let p mu be a polynomial, primitive polynomial with binary coefficients and the degree mu. And it's easy to see that the polynomial with binary coefficient modulo p mu is isomorphic to the binary extension field f2 to the mu. And by definition, primitive polynomial x is actually a generator of the underlying multiplicative group. So this gives us a way to build this generator function as follows. So for every non-zero point in the Boolean hypercube, we can represent it as a polynomial, right? We just translate the vector into the coefficients of polynomial. And we multiply this polynomial by the generator x. We obtain another polynomial in this field. And then we translate back to another point on the Boolean hypercube. This gives us a really nice map from the point u to next u, which is this, which is quite efficient. And now it seems gives us a way to do the rotation on the Boolean hypercube, right? So given the polynomial f, we just compose f with this next map. So however, also I want to say that next function is exactly like because x is a generator, it exactly allows us to travel using this next function to traverse the entire Boolean hypercube except the 0 points. So when mu equals 4, the cycle looks like this. However, there's a caveat of this solution because in the next function you can see in some dimension the formula is quadratic. For example, in here, B0 XOR 3, they have to represent, interpret as a like quadratic formula like B0 plus B3 minus B0 times B3. And because it's multilinear polynomial, it has more dimensions. After you compose the degree of the decomposed polynomial even has higher degree. So the degree even blow up, which actually affects the final protocol's efficiency. So how do we deal with this? The key observation is that actually we only care about the behavior and the values of this composed polynomial on Boolean hypercube. So we can just simulate it using Martin-linear polynomials. So the idea is this. So we recall this function, this next generator functions. We see that for all the dimension that has quadratic formula, they are all correlated with one particular variable, which is the last variable of the polynomial. Here is B3. So the idea is just to enumerate the value of B3 from only two options, 0 and 1, and after that, the entire next function becomes linear. So this gives a really good way to build this Martin-linear function as follows, right? So, and then now, a very, very good property of this shift function, which I call f-shift, is that first, it's Martin-linear, of course, and second, it's very efficiently computable, given only the oracle access of f. You just two evaluation of f. So you only need to, in the snark, you only need to commit to f instead of anything new. And also, it is consistent with the composed polynomial on the Boolean hypercube in terms of evaluations. To see this, like when B3 equals 1, you see that the linear term is triggered on, the left linear is triggered on, the right-hand side is turned off. Yeah, and it's turned off, and the result exactly matches. And similarly, when B3 equals 0, same thing happens. The left term is turned off, the right term is triggered on, and the result is still matches. So this gives a really good way that to do protocol on top of this new protocol, this new polynomial, rather than the original composed polynomial that has higher degree. So we can directly work on this Martin-linear polynomial directly, and without anything else, we just need the oracle from f. And this gives us a really good way to do have a linear enable us to have a linear time lookup protocol for this lookup relation. Yeah. So that's the high-level idea, and thank you so much. And then, yeah, just in summary, that we build a Hyperplonk, we extend it into lookup setting, and we build some Martin-linear polynomial commitments that can be plugins. And the paper has been published on ePrint. Welcome everyone to take a look and check all other interesting features that we achieve. Yeah, thank you.
Hi everyone, I'm Deveshwar, and I'll be talking about Zebra, which is an anonymous credential scheme with practical on-chain verification, which leads to implications for KYC in DeFi. So let's get started. So so Zebra solves the problem of on-chain access control, an example of which is KYC in DeFi. So long story short is that you only want users which have been KYC verified to access the DeFi contracts and not the other ones. And these, all these regulations are imminent, and they're going to be here soon. So let me give you a quick summary of what the prior work is in the area. So basically, all the prior work in this area is non-private. So what they do is they reveal the link between the wallet and the user identity to CA. And this information, even though it's with CA, it can even become public if the CA suffers a data breach. And there's a very simple solution to solve this problem, which is to use anonymous credentials. But existing anonymous credential schemes are expensive to verify on-chain. In particular, they cost $94 US on Ethereum in August. And our approach in this work is to use zk-snark-based AC schemes. And the high-level idea is to sacrifice prover efficiency for verifier efficiency. But the cost is still $8 USD. And this cost is per transaction. So you are incurring this overhead with each transaction. So in this work, what we do is we further reduce this credential verification overhead and in two ways. So for the first is we avoid this credential verification per transaction, and the second thing is batch verification. In this talk, I'll be focusing on batch verification because it's of more interest to this audience. Okay, so batch verification is pretty simple. I guess it's pretty similar. It's basically a roll-up where an aggregator gets multiple proofs from users, and it proves to the contract that it knows a valid proof for each user in the batch. Now, this is pretty straightforward, but there are some efficiency concerns. The first is that prior proof recursion works lead to high aggregator user overhead on EVM, and this is due to EVM artifacts in that it only provides native support for the BN254 curve. And the second problem is that there's a per user transaction data being posted on chain, like the snark part is bashed, but there's still user-specific data which is being posted on chain, and this limits like the improvement, the amortization to just 4x. Like you just get a 4x improvement irrespective of batch size because of this per user transaction data. And now, like I'll focus on the proof recursion part. So what is the problem with the prior proof recursion works? So the pairing-based approach has compatibility issues in that it requires a chain or a cycle of pairing-friendly curves, and no such cycle or chain is known for the BN54 curve. The accumulation-based approach has a linear verification step, which is although this step is it is independent of the number of users, it still is very expensive to verify on-chain or within a snark. And the Fry-based approach has a high user overhead and a high recursion threshold. So all this is all these works use R1CS, just like our solution. So now let's see what we do differently. So we take an approach where we recurse using a discrete log-based snark, which offers a square root verifier complexity as opposed to logarithmic or constant. And this is precisely the reason why this approach has not been considered, because square root is usually not concretely efficient. It does not lead to concrete efficiency. But in our setting, it fits very nicely, and basically the way we use it, it makes it amenable to efficiency. We use 2 layers of recursion, and we use 2 kinds of snark setup. One is a pairing-based snark over the BN254 curve, which is supported on Ethereum, and also a discrete log-based snark over the Grumpkin curve. And this is, and concretely, we instantiate them with Groth16 and Spartan. And basically, this is the setup. So the users create Groth16 proofs, which are then verified within Spartan, and then the Spartan proof is verified within Groth16, which is finally posted on-chain. Now, why this setup has better efficiency properties than the prior works? First, there are no compatibility issues because BN254 and Grumpkin form a cycle. So the green proofs can be efficiently verified within the blue proofs and vice versa. Then the user proofs have, creating the user proof leads to low user overhead and also low recursion threshold because they are pairing-based proofs. Then the computation that is being verified within Spartan is a SIMD computation, and it leads to multiple concrete efficiency benefits. The first is that the prover is 8 times faster, and the constraints for the verifier are also 8 times smaller. And finally, the Groth16 proof is posted on-chain, which is cheap to verify. So you get all these nice properties. Overall, we get a solution which can batch 512 users in just 1.5 minutes on a 64-core machine. And we expect, this is for R1CS, and we expect further improvements with Planck arithmetization, probably using things like hyperplanck. And overall, the improvements are 300x over pairing-based, accumulation-based is 9.3x in terms of aggregator overhead, and also similar improvements over Fry-based recursion. And finally, the user proof generation takes just 6 seconds, and we get up to 35x and 641x improvement over single credential verification using our batch verification solution. And that's it. Thank you for your attention.
Hello, I'm Uma, and I'm presenting on proof of consensus for the Ethereum Litecoin protocol, unfortunately cut off, from Succinct Labs. So the motivating question here is kind of what does a maximally secure and trust minimized bridge look like between different L1s? As you guys know, most bridges today are multi-sig bridges, and I think there was a talk earlier today on a ZK bridge as well. So I'll kind of go quickly through this concept since I'm sure you guys are familiar with it. But basically, the high-level idea is bridge security should be based on the same mechanisms validators use to agree on state, which is just verification of consensus. And then what we're doing at Succinct is we're one of many R&D orgs dedicated to building trust-minimized cross-chain communication using ZK snarks for proof of consensus. So why is verification of consensus hard? It's hard because, a blockchain like Ethereum, for example, during the course of coming to consensus will generate block headers and validator signatures. And then what you want to do is you want to verify Ethereum's consensus in the execution layer of another chain. So for example, Gnosis chain, or it could be any other EVM chain or non-EVM chain. But the problem with this, so once you verify consensus, what can you do? You have basically a light client running in the execution layer. of a different chain. And then once you have a light client with the headers, then you can prove any state about Ethereum in the execution layer of the other chain in a trust minimized way. So you can prove like someone deposited into your bridge contract with the state root, you can prove a transaction happened, etc. But in general, implementing consensus verification in a smart contract is very expensive and really difficult because you have to keep track of the current set of active validators and their stakes. And Ethereum in particular has like a lot of validators. And you also have to verify these signatures that might not have precompiled in the execution layer of the other chain. And so this is where ZK snarks come in. And so there's another factor with Ethereum, which is that there's 400,000 Ethereum validators, which is quite a lot. And the Ethereum R&D team realized that they need a separate protocol to enable support of light clients, regardless of snarks or not. And so they introduced this concept called the Sync Committee, which is a group of 512 validators chosen randomly every 27 hours. And these validators sign every single block header. And if enough validators sign off on a header, the block header is valid. And so the Sync Committee provides weaker security guarantees than full consensus itself, but it's much easier to verify in the context of a light client, which is what we did. And so, okay, the formatting is once again a little off. But basically, the Sync Committee, even though it's smaller and only has 512 validators, it's still actually too gas expensive to verify in the execution layer of a smart contract because you have to verify 512 curve additions on this BLS curve. And the BLS curve doesn't currently have precompiles in the EVM. And you also have to verify pairing, which is also super expensive. And so, the high-level idea that, for time constraints, not going super into details, you basically take off the expensive logic and validating a light client proof. So verifying the validators, verifying this BLS signature, you move that computation off-chain to a snark, and then you verify the proof on-chain, in our case, a Grot16 proof on-chain, and that's much cheaper. And so that's what we call proof of consensus. And so now I'm going to talk a little bit about how we actually did this for Ethereum Sync Committee protocol, so like a little more technical detail. So what we have is we have two snarks, one that actually verifies this BLS signature that we want on every single header update, and then we have another snark that actually verifies that the Sync Committee, which is like the group of validators, has rotated properly because the Sync Committee rotates every 27 hours. And our circuits are built in CirCom. So that's Grot16, and CirCom's made by Jordy and his team, who's actually was presenting earlier today. And basically, our circuits have over 70 million constraints, and they're really quite large. And so there's a lot of different primitives we had to make in order to verify this Ethereum Sync Committee. And so probably one of the most interesting parts of this is there's actually a lot of practical tips and tricks, like engineering oriented to dealing with these large circuits in CirCom. And one interesting fact that people don't actually talk about is, especially with like GPU proving our hardware, witness generation is actually the bottleneck for some of our circuits. And so we, to make this practical, had to focus a lot on really optimizing the witness gen. And so in CirCom, from a practical perspective, there's a few things you can do that actually greatly speed up your witness generation. One is CirCom has a parallel keyword to parallelize witness generation. And then in our circuit, we have to perform addition of 512 public keys to get an aggregate public key. And so what we did is we performed that addition or summation in a recursive tree structure, and that actually gave a huge speed up from 3 minutes of witness gen to around 1 minute, which is actually like a huge difference because our proving time is only 1 minute. And we have similar other tricks. We also have another trick where a significant amount of time in witness generation is spent in computing these witness variables that are constrained in CirCom. And elliptic curve math in CirCom directly is pretty slow and unoptimized. And so what we do is we compute these witness variables outside of the circuit and then provide those as an input into a circuit as kind of a hack. So these are some of like the practical engineering-oriented solutions that we had to come up with to actually speed up our circuit. We also have a few other tricks to reduce the cost of storing public keys on-chain that I don't think I have too much time to get into. But basically what we do is we map a snark unfriendly commitment to a snark friendly commitment. And then, the final thing I'll say is that we actually built all of this and then we integrated it end to end. And so we have an end-to-end working demo that you can check out at demo.succinct.xyz. It doesn't work on mobile because we don't have great front-end people. But you can go check it out today. It lets you bridge sysincs from Goerli to Gnosis chain. So we have a light client of Goerli running in Gnosis chain, and there's no multi-sigs involved. It's just verified directly on chain with our proof of consensus light client. And yeah, there's a lot of moving parts to our system that go beyond just the snarks. So this is like a system diagram of all the stuff that's going on beyond just the circuits. And so yeah, I think we will be releasing this more publicly this week. And audits are like probably the biggest bottleneck to a production deployment. That's all I have time for, but yeah.
Hey, I'm Wei from BigInt Capital Crypto, and today I'm going to be talking about security definitions of privacy-preserving payment systems. So I realized not everyone here is a cryptographer, so let me briefly explain how provable security is done in modern cryptography. So today we have talked a lot about constructions and proofs, of snarks, but actually underlying that, we need foundations of its syntax and security. So usually when we talk about cryptographic primitive, we need to first define what the algorithms should look like, meaning like what are the interfaces. And on top of that, we'll usually define security properties, usually in terms of formal security games. And then we can consider constructions and then prove them secure. So like to give you a little bit of an example of how this looks like for snarks. So the syntax for snarks, in particular for non-encrypted zero knowledge, has been studied since the 1990s. And its security notions, such as zero knowledge and soundness, has mostly been defined in the mostly 1990s. And some of the more advanced notions, such as simulation soundness, was later defined in the early 2000s. And on top of this, amazing work from 30 years ago, we have nowadays we can talk about constructions and proofs without really, thinking about how we, need to properly define security and syntax, because we kind of share this standard foundation of a common language for snarks. All right, so just to kind of like review a little bit, we need security definitions and syntax definitions before we can talk about constructions and proofs. So now let's talk about payments. So what do I mean by privacy-preserving payments? Well, privacy-preserving payments are effectively payment mechanisms that's operating on public blockchains where users can transact financially and have some form of privacy guarantee, right? So there's a long line of work on privacy-preserving payment systems, starting from the work of Zerocoin and Zerocash, as well as Ring CT, which is based on ring signatures, that is also implemented in systems like Monero, and also recent work like QuizQuiz and Zither. There's also industry works efforts on implementing these academic constructions to actually full functioning systems, such as different iterations of Zcash and Tornado Cash. So we now have a lot of academic approaches to building the systems, as well as industry realizations. You would think that maybe our foundations of definitions are really solid, but actually, if you look at what's happening in practice, is that every single work have its own security and syntax definition. Okay, so none of them are actually compatible. So this is the key question that I want to raise attention to. So let's look at an example of what I mean by everything's incompatible. So here's screenshots from papers, and defining what a privacy-preserving payment system is in terms of the list of algorithms that you should have. And I have circled the list of algorithms in red. You can see that they're pretty much all different. Okay, and there's some similarities in that they all have setup and keygen and maybe some form of verify, but the list of algorithms are non-standard. And in fact, if you kind of stare at what these algorithms do, we actually have a huge problem, which is that actually none of the definitions here list how transactions should actually get processed on the blockchain. Okay, so if you just like look at all the names on algorithms, none of them says how a ledger should process transactions. All right, so that's for syntax. Now let's talk about security. So the first caveat is that when we have different, when all this works are using different syntax, we cannot actually talk about security, right? Because the security definition won't be compatible. But nevertheless, let's actually try to compare them. So as it turns out, there's also a multitude of security definitions that have been proposed in different works. And the picture roughly looks like this. On top, you have different security notions, and on the bottom, you have different privacy notions. And as you can see, there's different notions that's considered in different work, and there's not really kind of a uniform, unified approach to considering security. And so this picture is just for the academic works, a select few of them. And so here's an example of the recent network upgrade for Zcash called Orchard, in which there's a security property called the fairy resistance is considered, and different approaches to achieve that security that was documented in the Zcash Orchard book. And to my knowledge, none of this is actually formally documented or kind of written up in a document. And in fact, if you look at their formal design doc, they don't really go into full detail. So there's a lot more to be desired in terms of formalization of the security properties. So let me just briefly mention one effort to unify the security definitions here. So as it turns out, if you kind of separate out the syntax and security into two different realm of concerns, one for users, one for ledgers, it's actually a lot easier to reason about these things. And so I think due to time concerns, well, I won't go into details here. So let me just go into the final remarks. So my talk today is mostly to raise attention to the problem that we have, which is that we want privacy preserving payments on blockchains, but we don't really have solid foundations for its syntax and security definitions. And even though there's some existing efforts to unify these security definitions, there's still a lot more work to be done.
Hi, I'm Brandon from Polygon Labs. Going to be talking about OpenZL, which is our new open source tooling for middleware and open standards for next generation of ZK apps. So basically, what we've seen over the past few years is basically this Cambrian explosion of ZK app tooling. So many different frameworks, so many different open source libraries, and mainly there are three problems. Of course, this innovation is incredible that we see in this space, but we see basically three main problems. The first is the lack of interoperability between common circuits and common tools that people use. Like if I write something in CIRCOM, I can't use it in Halo 2. Another problem is a large gap between proof system designers and language designers. So if you're building a language, you're building certain tools, you're building debuggers, you're building compilers, you're building sort of a syntax layer, and then you have people building on the proof system layer. And they have different goals in mind, and they have different design trade-offs they have to make. And so they're not necessarily talking to each other and can't make the best decisions. And of course, with the more code that we write, the more the security surface, and the more we have to spend on audits, and the more we're sort of fracturing ourselves. So OpenZL is one way that we can try and solve this problem. And the way it works is basically you have this universal gadget library that you can write code that executes in many different contexts, including contexts outside of, for example, a single proving system. So if I take all of my favorite proof system libraries out there, I can build a plugin for them into OpenZL, and also for languages. Any language I use, CIRCOM, Noir, Cairo, I can build a language plugin, and it can adapt to any of the circuits that I built that are compatible with the other proof systems. And then also auditing tools can plug in as well. And so we'll see sort of how this works. And okay, so the formatting is off here, but Basically, the way it works is you have this intermediate language called eclair. And what eclair does is it breaks down the way that we write circuits into 3 stages. So the highest level stage is called the compiler. And this is the place where this circuit gets executed, so the context under which it gets executed. Then you have the environment, which is something you can think of as like instruction set architecture for that circuit. And it provides hooks to change the implementation of the circuit depending on which context it lives in. So if it's in Plonk, for example, it can run certain constraints. But if it's in R1CS, where it's more optimal to do linear combinations, it's better in that environment. And so those hooks let you define where in the circuit those parts go. And then you have the actual symbolic gadget itself, where you run the circuit you want to define. And so we'll see an example here for just a simplistic example for Poseidon hash. So you can think of Poseidon as having, as being a function over an instruction set with 3 instructions, like the add round constants, the MDS matrix multiply, and the S box. And so given these 3 functions, I can write the implementation of Poseidon hash. But these 3 functions have different performance characteristics in different proof systems. And so as long as I provide those hooks for the specific plugins I'm using, I can get the most efficient Poseidon hash in all the different contexts. But I'm certain I can prove to myself that it's actually the same, it's going to give me the same output, and it's going to be correct in all of them. So this is sort of the way that you would write an eclair circuit, is you separate out this environment layer where you define where sort of this instruction set for your program. And so we can see, for example, in different contexts, let's say ArcWorks, if I've written my Poseidon hash function and then I plug it into the ArcWorks plugin, I get out a constraint synthesizer. So this is the sort of the primitive that ArcWorks uses to define circuits. And of course, I can go backwards as well. So if I have a constraint synthesizer, I can hook it into eclair programs and use it in other contexts that are not just for constraints. And the same exact code, right? So I wrote the gadget once, I then pass it through CirCom, and I get through a template API. So then I can call this circuit from other CirCom programs. And I get a hook into the CirCom compiler that lets me, directly access the witness generation. And then again, the same exact code I can pass through a tool like Picus and get back a symbolic program trace and static analysis report out that says, oh, maybe I have an under constraint bug or something. And again, it's all on the same exact piece of code that I'm just running through these different plugins. And another thing you get for free is that you can also just run it through the Rust compiler and get out a native execution of your circuit as well. So this is sort of the main idea of how Eclair works. It lets you express the single concept in any of these different contexts. And so we get a lot more security benefits for ourselves. We can understand that it's the same code running in all these different contexts. We don't have to rewrite for different proof systems. And we can link languages and compilers together. So if you'd like to play with OpenZL today, this is the GitHub repo. And we already have an ArcWorks plugin and a very large crypto like primitives library, encryption, signatures, aggregation schemes. And so, yeah, feel free to play with this, and we'll be making more plugins soon, and we hope you guys also make plugins for your part in the Cambrian explosion of ZK apps. Thank you.
Our last talk, but not the least, is by Sean.
Hi, my name is Sean Demantha. I'm here to talk to you about venture DAOs to support the entire ZKP ecosystem. Before I start off, I wanted to see how many of you have heard of an investment or a venture DAO of that concept, and how many of you have participated in one? Okay, a smaller fraction. So I'm going to start off just by saying hello, who I am. Here's some info in terms of who I am. I'm on the founding team of Hydra Ventures DAO. We are the first investment DAO fund of funds. We invest and incubate other investment DAOs in emerging tech ecosystems. I also have a background at DeFi and as a product manager at Google and YouTube. But enough about me. So what is a venture DAO? For those that that did not raise your hands to my first question. A venture DAO is essentially a decentralized venture fund. It takes communities, pairs them with communication tools, a treasury, as well as voting and smart contract structures so that, and potentially an LLC wrapper, so that you can trustlessly run a venture fund through a builder community. What makes the best venture DAOs are really builder communities. Before I get into that, we've come a long way in the last 4 years. a lot of the innovations in the space started off with what is called Moloch DAO version 1 smart contracts, which have gone all the way to version 3. How do we trustlessly operate an investment DAO using smart contracts? How do we build the layers, the trust layers on top of that to actually make that happen? All the way to today, a few months ago, where we founded Hydra Ventures DAO. As I mentioned, builder communities make the best venture DAOs. That means that they have strong deal flow. These are composed of multiple founders and operators in the ecosystem. Ideally, they are crypto native. They have the ability to diligence specific areas, and they are part of an emerging tech industry sector focus. These are a sample of investment DAOs put together by my colleague Peter Pan. By our accounting, there are less than 20 operational legal on-chain venture DAOs right now. What is the value add to founders? Say you're a founder in the space. Venture DAOs are a much higher value add to your cap table than your typical venture fund or angel investor. One, you can index the entire space. You can build a cooperative, almost like a cooperative trade group, where you as maybe individual participants who are competing on different aspects can cooperate together to align and move forward the entire industry segment. Two, venture DAO investing is naturally a social activity. It's an ability to strengthen your network across fellow founders and investors and build up the overall, upskill the overall ecosystem. Finally, there's less strings attached than your typical venture fund. You can quickly get funding in the matter of days and be able to have a larger network than your typical network that you might access from even a specialized venture firm with just a few analysts and partners. The question might be, why are venture DAOs a good fit for the ZKP system? Well, I think it addresses a few problems and opportunities in the ZKP ecosystem. One, I think one of the opportunities is that it's early. So it's very hard to aggregate all the different parts of the ZKP ecosystem. We've seen so many great presentations today covering so many different parts of the ecosystem. There are opportunities to look at infra choices, EVM versus non-EVM. We look at Starks versus Snarks, et cetera. Use cases, roles, privacy, distribution channels, and even hardware opportunities. I think there's also an opportunity with the venture DAO through the active investing together to start to address issues around how do you work together as a ZKP roll-up ecosystem in concert, in positioning compared to the optimistic roll-up industry segment. How can you grow new use cases? How can you address different concerns around regulation and the like as they come up? Finally, there's opportunities to really draw value capture back to the entire ecosystem. So you as a single founder are not always going to, your startup is not always going to make it to the point where you see profitable returns, but if you participate in an investment DAO, then that's an opportunity to index the entire ecosystem and learn from other founders in that space. So Hydra Venture DAOs, in summary, we're going to incubate a ZKP venture DAO. I'd invite many of you to join us. We started the first legal on-chain venture DAO with Metacartel Ventures, some of our co-founders. And we're going to start with the ZKP ecosystem and go to many other parts of the crypto and non-crypto ecosystems. If you're interested in joining, I'd encourage you to check out the link bit.ly/Hydra-ZKP DAO-interest. Or scan this QR code. Thank you.
Great. Thanks everyone for being here with us for this really exciting day. So this is the end of the workshop. Thanks everyone for being here. And we have reception here, and also, as I mentioned later on, there's a dinner downtown Berkeley as well. And so for people who are interested in learning more about ZKP, so please do sign up to our ZKP MOOC. So Dan's here, Chef is here, Yupeng is here. So go to zk-learning.org. And also for people who are interested in helping build the secure universal foundation for multi-chain interoperability, as I mentioned earlier, please do fill in the ZK Collective form, join the ZK Collective. Great. Thanks everyone. And also, right, so tomorrow is CESC. So we'll be at other parts of campus with a much larger room. at the Student Center. And also we'll actually have a ZKP session tomorrow morning as well. Shafi and Dan will be speaking there too. Great. Thanks, everyone. Thank you so much for being here. And right, we want to thank all the speakers, and also last but not least, let me thank the amazing RDI staff. So Jocelyn is here. Jocelyn is the deputy director of RDI, and who has really, put together and managed all these amazing logistics. And also, where's Samantha? Right, Samantha is also amazing staff member here. I don't know whether Jeremy is here, but okay, great. Yes, so thanks, huge thanks to RDI staff. Thanks.